Hi everyone. So in this section, I will introduce you with another data structure that is called a segment tree. Okay. So firstly, let's try to understand what type of problems a segment tree data structure can solve. For example, you are given an array and there is a range based query. Okay. So an example of range based query could be you want to, let's say, find a sum of numbers in the range A to B. Okay. So, or from, let's say, L to R. So you are given two indices, L to R, and let's say indices of this array are 0, 1, 2, 3, 4, 5, and it says okay, find the sum of elements from index, let's say 2 to 4. Okay. Or it could be find the minimum of elements from the index 1 to 5, or it could be, let's say, maximum of elements from 0 to 3. Okay. So this is a sum query, this is a minimum query, this is a maximum query. Similarly, you can have different types of queries, or maybe find the maximum subarray sum in the range L to R or something like that. Okay. So all these queries are called range based queries. So let's take example of min range query. Okay. So in min range query, you have to find out the minimum of the elements lying in a particular range. So you will be getting lot of queries like let's say what is the minimum in the range, let's say 1 to 4. Okay. So you know this minimum element is -5. So in the input you are given this array and you are also given this query. Okay. Or let's say what is the minimum element in the range 0 to 1. Okay. So in this range the minimum element is 1. So this is what you need to output. So a brute force way of doing a query would be you just iterate over L to R and you find out how much okay, so you iterate from L to R and you find out the minimum element. So that brute force query will actually take order of n time. Okay, so that's pretty bad. So if you have q queries and you have n elements in the array, so it will take order of q into n time for all the operations. So that's going to be inefficient. So another way what we can do is we can actually build a 2D matrix. Okay. And we can, if we know there are a lot of queries that are going to come, we can store answers of all the queries. Okay. For example, 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5. So what we can do, we can just pre-compute this table and we can store, okay, what is the answer of query 0 to 0? So that's going to be 1. What is the answer of the query 0 to 1? That's going to be 1. For 0 to 2 it's going to be 1, and for all elements onwards it's going to be -5. Okay, so you will have a table and these elements you can leave, so you won't be getting these queries because these positions denote L comma R. Okay, so and L is going to be less than equal to R. So you can do pre-computation in order of n square time, and then for each query, if someone says okay, what is the minimum element from 0 to 3, you just pick the element at this particular index, you can just do it in order 1 time. Okay, so this may be useful, but if the value of n is big, let's say n is 10 per 6, then you won't be able to build this array. Okay, so this is not a very good approach as well because it will not work for large numbers, large values of n. Plus it will not work if you have updates in the query. Okay, for example, someone says okay, apart from performing queries you have to perform updates as well. So updates would mean update the first element of the array and let's say make it as 13. So you need to update this element as 13, and once you update an element, you either you increment it or decrement it or put a new value on the top of it. So then you have to update this entire table. Okay, so that is again going to be a slow operation. So we will not follow this table based approach. So the third alternative that we will have is a segment tree data structure that we will learn in this section. Okay, so we can have table based approach. So we have learned the pros and cons of table based approach, and so it is actually useful if the value of n is small and you have only queries with no updates. And the third option, that is the best option to do, is it's a segment tree data structure. So this data structure can perform both queries and it can also perform updates. So let's learn about segment trees in the next video. Hi everyone. So now we will start with our discussion of segment tree data structure. Okay, so the problem that we are going to first see is the range minimum query problem. I will take this as an example to explain you this data structure. Okay, so the problem is you're given this input array with n elements, and let's say n is 5. So what you need to do, you need to find out, you are also given some queries. Okay, you are given queries from, let's say, L1 to R1. You want to find out the minimum element in the range L1 to R1. So L1 and R1 are indices in the array. Okay, for example, L1 is 1 and let's say R1 is 4, then the minimum element in this range is -5. Okay, from the range 1 to 4. Now we have to see how we can answer multiple queries by building a data structure. Okay, so a segment tree is actually a tree like data structure. So let me draw a tree here. This is the root node of the tree, and the root node of the tree will basically be responsible for the entire array. Okay, so it will represent the entire range of the array, that is from 0 to 5. And also it's a data structure that is based upon divide and conquer strategy. So what we will do, we say the root node stores the solution to the entire array, that is 0 to 5, and the left part of the root node will store the solution for the array that's from 0 to mid. Okay, so let's say we have this 0 to 5 is start to end. So in the left we will have from start to mid, and in the right we will have from mid plus 1 till the end. Okay, so that means this node will store the answer from the range 0 to 2, and this will store the answer from the range 3 to 5. And recursively we can further break it down. So this will be from 0 to 1, and this will be from only 2. Okay, and this will be for the node 0, and this will be for the node 1. And similarly here it will be for the range 3 to 4, and here it will be for the node 5, and here it will be for the range 3, and here it will be for the range 4. Okay, so now you can see each node represents a smaller answer of a smaller query. Okay, so this basically represents the answer of the query from 0 to 2. So we will actually pre-compute all of these answers by building this kind of a tree. Okay, so building a tree is one step in the segment tree. So now let's see how we can actually fill values in all the nodes. So let's say, so if you want to find out the minimum of the range 0 to 5, so that is going to be easy if you know the minimum of the range 0 to 2, and if you know the answer for the range 3 to 5. So that means firstly we need to build the child nodes, then we can build the parent node. So that's why we will build this tree in a bottom up manner. Okay, so it's also called as post order traversal that we will do in the code. So let's build this tree in a bottom up manner. So because the leaf nodes are the nodes that are easiest to compute, so that means if you want to compute what is the minimum of 0, so that's the element at 0, so that element is 1. What's the minimum at 1? So that's 3. What's the minimum at 2? That's basically 2. And now once you know leaf nodes, you can actually start building the parent nodes as well. So minimum of 3 is -5. I will just put these values also there. So minimum of 4 is 6, and minimum of 5 is 4. Okay, so that means query from 5 to 5. Okay, so now once you have the values in the bottom nodes, now you can fill the values here. So at this point I can say, okay, this is the minimum of 0 and 1 is going to be the minimum of the left part and the right part. So this is going to be 1, and here it's going to be 1, because the minimum of left and the minimum of right, and here it's going to be minimum of left and right, it's going to be -5, and here it's going to be minimum of left and right, that's going to be -5, and here it's going to be minimum of left and right, it's going to be -5. Now you can see that in this tree we are storing answers to some smaller queries. Okay, so every node represents a sub problem that we have actually computed. So this is what is the meaning of building this particular kind of a tree. Okay, so in segment tree we will perform different operations. One operation will be build, another operation will be query, and another operation will be update. So we will come to these two operations one by one, but let's first focus more on the build operation. So now we actually have to build this tree as well. Okay, so that means we need some kind of data structure to store this kind of a tree. So what we will do to build this tree, we will actually use a array like data structure, because you can see it is going to be a balanced tree, almost like a balanced tree, because the left part and the right part are going to be almost equal. Okay, because we are always breaking at the midpoint. So what we can do to make it to store this particular tree, we can use a array like data structure. Okay, and also we know that a tree contains hierarchical information. For each node, you know what is the parent of this node, and what is the children of this node. So let's see how we can store this hierarchical information in the form of a array. So for that, I'm going to assign numbering to all the nodes in the tree. So let's say the root node will get a number 1, the left child will get a number 2, it will get a number 3, it will get an index 4, it will get an index 5, it will get index 6, 7, 8, 9. Now here I will not give index 10, because if this node had two children, so indexing is going to be linear. So those indexings were to be assigned to the children of this particular node. Since they are absent, so we will skip these two indices and we will give an index that is going to be 12, and that's going to be 13. And similarly, we could have given 14, 15 at this particular point, but these nodes are not present, so we basically skip those indices. So why this property is important? This is important because given a node, let's say given a node index I, let's say given the node index is 6, you want to find out what is the index of the left node and what is the index of the right node. So if we follow this particular order, you will see it follows this property. If the node index is I, the left node is present at 2i and the right node is present at 2i plus 1. Okay, and similarly you can hear for the node 6, we have the left child as 12 and the right child as 13. So that's why we need to maintain this relationship in the array, and that's why we are giving indexes like these. So let's build an array, and we will start from index 1. The 0th index we are leaving. Okay, so the array should now look like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, now you can see this array is called a tree array. Okay, so this is actually your segment tree, and what information it will store? It will store -5, 1, -5, 1, 2, -5, 4, 1, 3. Okay, so in the 9th index we are storing 3, and 10th index will be garbage, 11th index will be garbage, and here we store -5, and here we store this element that is 6. Okay, now this is your actually segment tree array, and this index is left as it is. So now you can see if your original size is n, then this tree array size is much larger than n. Okay, so approximately this size is actually 4n plus 1. Okay, so this is an approximate size. So all the arrays can fit in a tree array of size 4n plus 1, and you can see it is also linear in terms of n. Okay, so I'm not discussing the proof, but this is a good approximation of the maximum size that you have to take for converting any array into a segment tree. So let us first focus how to build the tree, and then we will come to the query part in the next video. Okay, so now I will write the code for building the tree. Okay, so let's begin. So what we will do, we will first construct an array, and let's add some elements in the array that we have taken: 1, 3, 2, -5, 6 and 4. So these are the elements in the array, and number of elements is also given as size of a upon size of int. And after that, what I need to do, I need to construct a tree array. Okay, so let's say this tree is new int of 4 into n plus 1. So this is my tree array, and I can call the build tree function with this particular array. Okay, so we need to write this function that will actually fill our tree array. So let's say we have this function void build tree that will get the original array from which we want to copy the elements in the tree. We get a start and an end, and we will also get the tree array, and we will also get the index on which we are working on a tree array. Okay, so now let me tell you what terms we are using. So if you are at particular node index, so that node is responsible for a range start to end, and you need to find out what is the minimum element in this particular range. Okay, that you need to fill. So what we will do, we will adopt a recursive strategy. On the recursive strategy, we will have a base case. In the base case, you will see start and end will become equal. Okay, and in that case, what you need to do, you need to say, okay, at whatever index you are, the tree of that particular index should store the value that is there in array of start. Okay, so at this point, if you are reaching, you are pointing at one particular element of the array. Okay, so start and end both point to, let's say, 6. So tree of index should contain 6. So we will recursively try to break down the problem until we reach the base case, and then we will build the tree in a bottom up manner. So let's write the base case here. If start is equal to end, then we can say tree of index should be equal to array of start, and we can return from the base case. Otherwise, we have a recursive case. Here you can find out the midpoint. So midpoint is start plus end by 2, and then you, in order to build this node, okay, in order to build the node tree of index, what you need to do, you need an answer from the left, and you also need an answer from the right. So firstly, we will build the left subtree. Okay, so if you want to put something here, firstly you need to build the left subtree, and you also need to build the right subtree. So that will be built using the function called build tree, and we need to call on the left part. Okay, so for the left part, we need to query from, we need to send the range from start to mid, and for the right part, it should be from mid plus 1 to end. So let's do it. So we can say, okay, build the left tree, that is array, start from start, go till mid, and give the tree array, and the index of the left node will be 2 into index. Okay, and the index of right node will be 2 into index plus 1. So that's what we are going to give here. It will be 2 into index, and build the right part, it will be array, it will be mid plus 1, and then we have e tree and 2 into index plus 1. That's it. And now once you know this left tree has been built and the right tree has been built, what do you need to do? You need to put the minimum element. Let's say this minimum element is 1, and let's say this minimum element is -5. You need to put the minimum of left and right at this particular node. So it will be minimum of tree of 2 into index, that's the left node, and tree of 2 into index plus 1, that's the right node, and we can say return. Okay, so that basically completes our build function, and you can say it's a post ordered reversal. First we build the left subtree, right subtree, and then we build the current root node. And what you can do now, you can call this build function from the given parameters. Okay, so we need to give the array, that is a, starting point is 0, ending point is n minus 1, and we have the tree array, and the starting index of the tree array that I am taking is going to be 1. Okay, and let's also print the tree array, and we should get the same array as we have drawn in the diagram. So I starts from 1, I goes till less than equals to 13, I plus plus, and I can see out tree of I. Okay, so let's run our code, and you can see we are getting this array, and that is exactly same as our input array. And you can see the indices 11 and 12, they also contain a garbage value, as I said. Okay, So that's all. We will see queries in the next part. Hi everyone, so now we will discuss how we can perform queries using the segment tree data structure that we have built. Okay, so this is our tree, and now suppose we get a query. So someone says, okay, give me the minimum element in the range 0 to 5. Okay, so let's say the first query that we are going to get is the query from 0 to 5. So what you need to do, you need to start traversing from the top of the tree, and you need to check what range it contains. So it contains a range from 0 to 5. So clearly that means this contains the minimum element, so you directly return the answer from here. Okay, I got an answer that is going to be -5, the simplest form possible query. Okay, so similarly you can have so this case is called a case of a complete overlap. Okay, so let's call this case as case 1, and in this case you have complete overlap. So let's say in that case, if your query range is from QS to QE, and the node at which you are standing, that also has a range from S to E, such that S is equal to QS and E is equal to QE. In that case, you just need to return the answer that is stored at that particular index of that node. Okay, so you just need the answer. So index in this case is 0, so we return tree of index. So that is the case 1. So let us discuss another case where you can have a complex query. For example, you get an query in which you need to find out the minimum element in the range, let's say 2 to 4. Let's say this is another example of query. So you need to find out, okay, what is the minimum element in the range 2 to 4. So again, this answer is minimum 5, -5. So what do you need to do? But now you can say you cannot directly extract the answer from the top of the root node. So what you will do, this is a case of a partial overlap. So why partial overlap? So your node contains an answer from S to E, that is from 0 to 5, but you need an answer that is 2 to 4. That means partial part of the node range contains an answer to the complete query. Okay, so or you can say this query lies partially in the node range. So what you will do in such a case, you will make two calls, one on the left and one on the right. So what you do, you make a call at this particular node, and you also make a call on this particular node. Okay, so at this node, you say this node contains an answer in the range 0 to 2. Okay, so we have 0 to 2, and the query ranges from 2 to 4. So 2 to 4. So this is also a case of a partial overlap. Okay, so what you will do, you will again make two calls, one on the left and one on the right. Okay, so you are sending this query, I want the answer from 2 to 4, I want the answer from 2 to 4, I want the answer from 2 to 4, I want the answer from 2 to 4. Now let's try to analyze what happens at this particular node. So at this particular node, you see we have a case in which the node range is from 0 to 1, but the query range is from 2 to 4. Okay, so that means there is a third case, that is a case of a no overlap. Okay, so what do you do in such a case? So you're asking this node, give me the minimum element in this part. So since this range does not lie in this part, so what do? You can return infinity. You can say, okay, I didn't find anything, so this value is going to be infinity. And what do you do? So you send a range 2 to 4 to this node, and what happens here? So your query range is 2 to 4 and your node range is just 2. So that means this range lies completely inside the query range. So what you will return? You will actually return the minimum element of this range, that is going to be 2. Okay, so at this particular node, what you will do, you will try to find out, okay, what is the minimum of the left part and what is the minimum of the right part. So from the left you are getting infinity and from the right you are getting 2. So this node will return 2 to the parent node. So 2 goes here. Okay, and now you also pass the query on the right hand side part, so you get a query from 2 to 4, but at this point you see it is of this form, it's of the form 3 to 5. So in such a case, what you will do, you can see you have 3 to 5 that is there in the node range, but you want the answer from 2 to 4. Okay, So 2 to 4. So that means this node range contains an answer to the partial part of the query. So again, it's a case of a partial overlap. So you make a call on this node, you make a call on this node, and at this node you see it's a example of no overlap. So you return infinity from this node, and at this particular node you see what happens. So you want the answer from 2 to 4, but this node contains the answer from 3 to 4. So this will be a case of a complete overlap. So that means in case of complete overlap, you will just return this answer that is going to be -5. So at this node you get two answers, one is -5 and another is infinity. So you return the answer that is -5 to the parent node. Okay, and at this node you are getting two answers, that is 2 from the left and -5 from the right, and you can see the minimum is going to be -5. So this will be able to return the minimum answer that is going to be -5. Okay, so we have now seen there are going to be three cases when you are going to make queries: a case of a complete overlap, a complete case of a partial overlap, and case of a no overlap. And this is how you can resolve all queries. Okay, for example, let me give you one more example in which, let's say you want to find the minimum in the range, let's say 4 to 4. Okay, so what you will do, you have this 4 to 4, it is a case of a partial overlap, you go on left and you go on right. It's a case of no overlap at this point, so you just return infinity here. At this point it's a case of a partial overlap, you go on the left and you go on the right. It's a case of no overlap, here you return. At this node you see it's a case of partial overlap, you go on the left and you go on the right, and here it's a case of no overlap, so you return infinity from here. And here once you reach this node, you see the minimum element is 6. What do you return? You return 6. So here from this node you return the minimum, that is 6. From this node you return the minimum of 6 and infinity, that is 6. And from this node you return the minimum of left and right, that is infinity and 6, that is going to be 6. So this is how you get the minimum element for the range 4, 4 as 6. Okay, so let me briefly give you a recap of all the cases. So first is a partial overlap. Okay, in partial overlap, if this is your node range, that is from start to end, your query range can be of the form QS to QE. Okay, so a partial part of the query lies in this range, or it can be of the form QS to QE. Okay, a partial part of the query lies in the range. Okay, second is a case of a complete overlap. So in complete overlap, what is the case? So if you have a range QS to QE, what you can have is, you can also have something of this form. Okay, so I discussed the case when QS and QE are exactly same. So this is one case. Another case is the entire part of the node range lies in the query part. So this is an example of a complete overlap. So carefully you have to distinguish these two cases. And third is no overlap. So you have node range S to E, and let's say your query range is like this, or it is of this form. Okay, so this is the case when QS is greater than QE, and this is the case when QE is less than QS is greater than E. Okay, so these are the three cases. And in the partial overlap, what we have to do, we have to make call on both sides. Okay, and in case of complete overlap, we have to return from the node. And in case of no overlap, we have to return infinity or some other value depending upon the question that you are doing. Okay, so if it could have been find the maximum element, in that case you could return int min minus infinity. Okay, if it would have been sum of elements, you could have returned 0. Okay, so that will depend upon the type of question that you are going to solve. So I hope these cases are clear. Now we can proceed with the implementation part. So what we will do, we will write a function called query and we will get the tree. So now we do not need the array because the queries will be performed on the tree that we have already built in the first step. So we have a start, we have a end, we have query start, we have query end, and one we have index. Okay, so SS means start of segment tree, node and end of segment tree node. Okay, so this is basically the range that node is storing. Okay, so let me just clear. So this is SS to SE, and you are getting something QS to QE that you want to query. So we will make corresponding checks. So let's first write a case of a complete overlap. So in complete overlap, we can say if SS is greater than equal to QS and SE is less than equal to QE, what we will do, we will just return the node at which we are currently standing. So currently we are at the node whose index is index. Okay, then we have the case for no overlap. So in that case, if QE is less than SS or QS is greater than SE, we can say return int max. That's it. And finally, we have partial overlap. So we need, in that case, we need the answers from the left and we need the answers from the right. So mid is going to be start plus end by 2. And we can say, okay, answer from the left will be query, and we give tree and the required parameters. Okay, so the index of the left node will be 2 into index, and for the right will be query tree. The range will start from mid plus 1 till SE. The query range will remain same at all the nodes. So right node will be 2 into index plus 1, and here you can return minimum of left and right. That's it. Yes, so it should be query. Okay, so now let's write the code to read some queries. So let's say int q scene q, we will read some queries. Okay, so while q minus minus, we can say, okay, give me L to R, and I will make a query in that particular range. So cout query of what we need to give, tree SS SE, so 0 n minus 1 L to R, and the starting index is going to be 1. So let's test our code. Okay, so let's say I have 3 queries. Let's say a query in the range 4 to 4, so we get 6. 0 to 4 we get minus 5. 0 to 1 we get the element 1. So you can see it's working fine for all types of queries, and this is how we can query in the segment tree. Next we will see is how to do update. Hi everyone, so now we will discuss updates in segment tree. Okay, so when you talk about updates, there can be 2 types of updates. So first type is a point update, in which you will update one element, and another kind of update is range update, in which you will update a range of elements. Let's say if you want to update all the elements from L to R and you want to increment by with an, let's say, value of plus 10. And point update means you're given an index I and you want to increment it, let's say, by a value of plus 10. So firstly we will discuss point update, and in the next video we will discuss range update. So let's say you are given this index, let's say this index is 3, and I say, okay, update this index and make minus 5 updated by a factor of plus 10, so you make it as 5. Okay, so what will happen in this case, you get a query. Okay, you get an index, let's say that is 3, and you also get, okay, the value, the increment that you need to do. So increment that you need to do is, let's say, 10. So what you do, you see at this point, okay, minus this 3 lies in this particular range. Okay, so what you will do, you will make a call on the both left and the right. So it's kind of like a partial overlap case. Okay, or you can say, so 3 lies in this particular range. So in such a case, what you do, you make a call on the left and you also make a call on the right, and at this point you say, okay, index 3 is there, it does not lie in this particular range. So you come back without doing any update, and at this particular point you say, okay, 3 and 5, 3 lies in this particular range. So you make a call on the left, you make a call on the right. So but you see 3 does not lie in the range 5, so you just come back from this point. At here you see 3 lies in this particular range, so you make a call on the left, you make a call on the right, so you reach the leaf node. And again at this node you see 3 does not match with this index 4, but it matches with this index 3. So what we will do, we will try to update our tree in a bottom up manner. So what we will do here is, we will say, okay, now this minus 5 will be incremented as minus 5 plus 10, and this will become plus 5. So we make this value as plus 5, and while going back, what we do, we compare the minimum from the left and we compare the minimum from right. So right says the minimum is 6, the left says minimum is 5, so we make this minimum as plus 5. Now you understand why we are calling on the right as well, okay? And at this particular node, you have an answer from the left, that is plus 5, and you have an answer from the right, that is now plus 4. So at this node, you will update the minimum to be plus 4. And at this node, when you made a call on the left, and what you will return, you will actually return the minimum element from the left. So that is going to be 1. And from here, you return the minimum element, that is 4. So this element will be now 4. So what happens is, the minimum element is 1, right? So the minimum of 1 and 4. So this is going to be 1. So now you can see if this element is plus 5, and if you do a query, let's say from 0 to 5, the minimum element is actually 1. Okay, or if you do a query from 3 to 5, the minimum element is going to be 4, and we have actually stored this element at this particular location. So that means starting from the root, starting from the leaf to the root, we will update all the nodes where the element is updated. Okay, and it is also possible that some of the nodes may not get updated. That's also possible. Okay, let's see one more example. Let's say what you are saying is, let's say you want to update the second index and you want to make it, let's say you want to make it as 12. So what will happen in this case? You start from here, you make a call on the left, you make a call on the right, but 2 does not lie in this particular range. Okay, so the index 2, I'm talking about this index, and we come here, so it lies in the range. We make a left call, we make a right call. So in such a case, what we'll do, you will say, okay, let's make this element as 12, and let's return the new minimum from the left and right. So the minimum from the left is 1, the minimum from the right is 12. So this node will still remain 1, and when we come back to this particular node, the minimum from the left is still 1 and the minimum from the right is minus 5. So we say, okay, this minimum is still minus 5. Now you can see how we are able to perform this update. So while doing an update, you will basically do a bottom to top thing, and during this process, some of the nodes may get updated, or all of the nodes in the path may get updated. Okay, so that's the whole idea of doing an update. Now we will see the implementation. Okay, so let's go into the code and write a function. So let's say the function is void update, and we get the tree, we get the starting point of the range and the ending point of the range, followed by the index in the array where you want to perform the increment, and the index of the tree node. Okay, so here what we can do is, we can first have the case where the I is out of bounds. Okay, so out of bounds means, for example, you are at a node where you have, let's say you are at a node which stores the range 3 to 5, and you say, okay, I'm coming with an index 2 at this node. So 2 does not lie in this particular range. Okay, so that means we have this particular range, and your point update lies either before the starting point or it lies after the ending point. So this is SS, this is SE, and this is my index. Okay, this is my I. So what I can do, I can say, okay, if I is greater than the ending point or I is less than the starting point, I will just return. Okay, I will just return. I will not do anything at this point. And in the leaf node, I can say, okay, if SS equals to SE, so that's the case for the leaf node. What I will do, I will say tree of index should be updated by that particular increment that I'm getting, and I will return from that node. So that's your base case. Otherwise, what we need to do, we need to see from the left, we need to see from the right, and we need to update our current node by taking the minimum of those two. So we can say mid equals to start plus e by 2. We will pass the query to the left subtree by calling this function update node tree ss mid plus 1 I increment and 2 into index, and we will also pass the query to the right subtree by doing this sorry, this should be mid, right? And here we will have mid plus 1 and SE I increment and 2 into index plus 1. So once we are done with this, we need to update the value at the current node. So that's what we do. So we go left, we go right, and we now update the current root node. So that's going to be minimum of the left, that's 2 into index, and tree of 2 into index plus 1. That's it. And here we can say return. Okay, so this is SS plus SE. Right, so this function should be update node. Okay, so what we can do, we can first call an update node function. Let's try to test our code. So I can say, okay, let me update two nodes. So one is we give tree 0 n minus 1. Let's say we want to update this index 0 1 2 3. Okay, so the third index and increment of, let's say, plus 10, and the starting index of the tree, that's going to be 1. Okay, so now let's run some queries after doing an update. Let's say I want to run 3 queries. One is from 0 to 5. So we get the minimum element as 1. That's there. And let's get the minimum of 1, 2, 3. Okay, minimum between 1 to 3. That's 2. That's correct, because now this element is plus 5. Okay, and let's get the minimum of last 2. That's 4 to 5. So that is 4. So you can see update function is working fine. And one last thing that I want to talk about here is the complexities. Okay, so clearly now you can see what would be the complexity of the build operation. So in build, what you do, you basically fill this entire array, and since this array is of linear size, so you can see the complexity to build the tree is order of n. And let's see the complexity of doing a query. So in query, what you do, you basically kind of traverse the tree from top to bottom, and you do it in, let's say, 2 or 3 branches. Okay, and each branch contains log n number of nodes, so it will be order of log of n, and since this tree has a height of log n. And another is your update operation. So update operation is similar as query operation. What do, you traverse the tree from top to bottom in just 1 or 2 branches, so it's going to be order of log of n. So you can see the queries are now pretty fast. It's better than doing a linear query in order n. Okay, so if you just do a brute force thing, the query will run in O(n) time, but here we are running the query in log n time, and log n is far better than order n approach. Okay, so I hope this is clear, and thanks a lot. Hi everyone, so now we will discuss how you can perform range updates in a segment tree. Okay, so now you are given a range, let's say L to R, and you are asked, okay, update, let's say, all the elements in the range 3 to 5 by a value of plus 10. Okay, so this element will become 5, this will become 16, and this will become 14. So what you need to do, you come to this particular point, okay, and you see, okay, your query that you now have is going to be let's say 3 to 5. Okay, so what we will do, we will pass on this query. Okay, so if this range contains a part of the query, okay, and or it contains the entire query, so we will pass this query on both left and right. So we pass this query here, so we get 3 to 5, and at this particular point we also get this query 3 to 5. Now you can see at this particular point it's a case of a complete overlap, but we do not need to stop at this particular point. If we just update this value by a factor of plus 10, that would actually will not update these values as well. Okay, so these values need to be updated, because if someone queries 3,3, then if you just stop at this particular point, then it won't make sense, it will give you wrong answer. So that it means that you need to propagate the queries to the both end of the tree. Okay, but there is a special case here, that if your range does not overlap with the node range. So node has a range 0 to 2, but your updates are based in the range 3 to 5. At this point you can say, okay, return no node in this particular entire subtree will get any update. Okay, so in case of a partial or a complete overlap, you have to go till the end of the tree and you need to update all the possible nodes. So that's the idea here. And you cannot use, okay, another way could be you call point updates in a linear fashion on every node, but that will take more time. So if you have u number of updates, and if you call, okay, call and point update on 3, call and point update function on 4, call point update function of 5, that will be u into log n. Okay, but that's not the way that we are going to do. So we are just going to traverse the tree only once. Okay, in the worst case, if let's say all elements are updated, so we will update all the elements in the tree, okay, starting from the leaf node till the top of the tree, and the worst case complexity of update range will be order of n. Okay, so let's see how we can implement this as a function now. So I will quickly write the code for the same. So firstly we need to check the case where our query is out of bounds. So if your left is less than left is greater than SE, okay, or right is less than SS, we will say return. Or we have a leaf node, that's like a base case, and otherwise we have the recursive case in which we have to make a call on the left tree and the right subtree. So this is a case of a no overlap. For example, if you come to a node and you see, okay, this is SS, this is SE, your range update is either lying here, that is L is greater than SE, or your range update is lying here, that is your R is less than SS. Okay, so in such a case, so this is L to R. So in this case, R is actually less than SS. So that means no need to update that node or its subtree. Okay. Otherwise, if we are at leaf node, if we are propagating the query downward, and if I reach a node where SS equals SE, that means we have to update that node by the following increment, and we can return from that node. In the recursiveness, it's easy. We need to find out the midpoint. So SS plus SE by 2, and we need to call the update range function on the left. So we get this, we give this tree SS mid L R 2 into index, update range right, so tree mid plus 1 SE L to R. Okay, so one more parameter is there. We have to give increment also. Okay, so increment and 2 into index plus 1. That's it. And now you update your current node. That's minimum of left and the right, 2 into index and tree of 2 into index plus 1. That's it. And you can return from this particular point. So this completes our range update function. Okay. So remember, do not put this case on the top of this case, because the first step should be you need to check out of bounds. If your leaf node is out of bounds, then you do not need to update it. So the order of cases is also important. Okay, so the first case should be the out of bounds case in this example. All right, so we can build our code, we can test our code, we can say, okay, update range, let's give the range, let's say update all the elements from the range 3 to 5 by a value of plus 10. So let's do queries now, 3 queries 0 to 5, and let's say what's the maximum element. So in the 3 to 5 range, now the maximum element will be this much. Okay, 5, and you can test 0 0 1. All right, so you can see this is working fine, and that's all for this video. Hi everyone, so in this video we will talk about lazy propagation. That's an optimization that we can do to perform efficient range updates in segment tree. Okay, so we can do this range update in order of log n time using this lazy propagation optimization. Okay, so let me quickly discuss the idea. So the idea is postpone the updates to the descendants of a node until the descendants themselves need to be accessed. Okay, so let's see what this statement means with the help of a very simple example. So let's say you have a segment tree and the root node stores the answer for the range 0 to 5, let's say. Okay, and there is a query in which you need to update all the elements of the range 0 to 5 by an fact a value of, let's say, plus 10. So what you will do in the normal case, you basically iterate over all the nodes of the subtree, all the nodes of this particular tree, and you update them, and that takes order of n time. That's what we have seen. But in lazy propagation, what we will do, we will say we do have the same tree, okay, and we will postpone our updates. So we say, okay, you need to increment all the elements of this range 0 to 5 by plus 10. We will say, okay, we have noted this change in this entire range, we update the root node, but we say we will not update the entire subtree, both on the left and both on the right, but we will tell the subtree there is an update that is pending to be applied. So this update will be applied later. We will apply this update later. So what we will do, on every node we will store one another value that is called as the lazy value of that particular node. So in such a case, the left child of root and the right child of the root will have a lazy value of plus 10. That means all the nodes in the left subtree starting from this particular root node needs to be incremented by a value of plus 10, but we will do that increment once we need the answer for that particular node. For example, someone says, okay, I want to find out the answer at this particular node. In that case, you will traverse this tree from top to bottom and you will adjust all the lazy values while traversing this tree. So how you will adjust, you will say, okay, 10 will be added to this node, and let's say this answer was, let's say, initially 5, now it becomes 15. Let's say this answer was 6, and you will pass on the lazy value to this particular node. So once you reach this node, you say, okay, the old answer was 6 and now this answer will be 16. So as you need to access that particular node in some other query, you will adjust the lazy value. That's what it does. Okay, so this is a simple idea that can actually make your queries which were running in order of n time into order of log n time. So let us discuss it in little more detail with the help of some examples. So let's say this is our tree that we have already used, and let's try to perform some lazy updates in this tree. Okay, so let's see how we can perform some lazy updates. And these updates can be, you need to update the element, you can also perform queries. So I will give you an example in which we are dealing with both updates and queries. So let's say in the first query you get an update all the elements in the range, let's say 0 to 2, by a value of plus 10. Okay, so what do you need to do? So initially you have lazy value 0 that is attached with every node, and this is initially 0. So you have an update in which you are getting this update 0 to 2, and you need to increment by every element by 10. So that means the updated array will look something like this: 11, 13, and then you have this 12, and minus 5, 6, and 4. So this is the meaning of this update. But let us see how we can apply this update on a tree, and let's apply a lazy update. So we come to this node and we get the range as 0 to 2. So what we see, 0 to 2 lies in this particular range. Okay, so what we will do, we will call on both sides. So we make a call on the left and we also make a call on the right. So at this node we have this range 0 to 2, but the range represented by the node is 3 to 5. So you can see there is a case of no overlap. So what we do, we just come back from this node without doing anything. So we will return. Okay, so let's see the case when we go to the left. So at left node we again have this range from 0 to 2. So what we do, we say, okay, 0 to 2 matches exactly with this node. Okay, so that means there is a case of a kind of a complete overlap. So what we do, we update this particular node. We say, okay, the minimum answer will be now 11. So we update this node. So we say, okay, node plus equals to the increment, and we will pass lazy value to the children, pass lazy value to the child nodes. So we have two child in this case. So one is the left child. So we update this lazy value as plus 10 and we update this lazy value as plus 10. So this lazy value basically means the entire left subtree, this tree in red, and this tree needs to be updated by a value of plus 10 when we need to access any node in this particular tree. Now you can see. Okay, so this is the meaning of these lazy values. So this is how we will do the first update. So you can see we just traversed this much part of the tree instead of traversing all the nodes in this entire subtree. Okay, so you can see it will actually help you to save some time in doing this kind of a update. So let us add some more queries in this tree, and let's say this time your query is u2, and in the u2 query you get the index from, let's say, 0 to 4, and let's say you want to update all these indices by plus 10. So that means all these values need to be updated by plus 10. So it becomes 21, 23, 22 plus 5 and plus 16, and this is 4. So what do? You get this query here. So the query is from 0 to 4, and you can see this query lies in this range 0 to 5. So what do? You make a call both on the left and you make a call on both on the right. So we go on the left, we say okay, query is from 0 to 4, and we go on the right and we say okay, the query is from 0 to 4. And now you can see 0 to 2, it also lies completely in the range 0 to 4. Okay, so we have the range 0 to 4, but this node represents 0 to 2. So if you need to update all the elements of 0 to 4 by plus 10, that means all the elements of 0 to 2 also need to be updated by plus 10. So what do? So you make this value as 21, that's the update you apply here, and you pass on a lazy value to its children. So its children already has a lazy value of plus 10, but this value will now become plus 20, both on the left and both on the right, and you go back from this particular tree. Now you come on the right hand side part, and here you see this represents the answer from 3 to 5. So there is a case of an overlap. Okay, so here also you can see there is an overlap in these ranges. So once you find an overlap, you make a call both on the left and both on the right. So you come at this particular point. Okay, so at this node you can see 3 to 4 completely lies in the query range. So that means you just need to update the value at this particular node. So we will update the value of this node by plus 10. So it will make this value as plus 5, and you pass a lazy value to the children. So it will be plus 10 and it will be plus 10. So these nodes now have the lazy value, and here these subtrees have the lazy value. Okay, so this is how you apply the second update that we have drawn. Now let's apply another update in which you need to update only the first element. Okay, so the first element of the node you need to update, and let's say you want to increment it by plus 5. So this will now become 21, 28, 22, 5, 16 and 4. So you need to update this element. So what you will do in this case, you will start traversing the tree from again top to bottom. Okay, so the range is 1, 1. You go on the left, you go on the right. Here there is a case of no overlap, so you come back, you go on the left, you go on the right. There is a case of no overlap, you come back and you go on the left and you go on the right. But once you are going from a node that carries a lazy value, you first need to update that particular node. Okay, so what you will do, you are coming to this node, so you will update the value of this node as 21. So this becomes 20 plus 1, 21, and then you go on the left and you will pass on the lazy value to its children. So it will become plus 20 and it will also become plus 20. So now let me just show you. So this lazy value will now become 0. The lazy value at this node, it will become 0, and it passed the lazy value to the children. Okay, so now these nodes have a lazy value. Okay, and since you need to update this node, right? So you need to update this node. So the answer at this node should be 28. So now you're carrying two values. One is the increment that you need to do. So that increment is plus 5. And another is the lazy value. That lazy value is 20. So at this node, you will perform two updates. So one will be, firstly, you need to resolve the lazy value. Okay, so if you resolve the lazy value, what do you need to do? You need to do, it's 3 plus 20. That makes it as 23. And then you say, okay, I was looking for this node and there is a case of complete overlap from 1 to 1. So I will update this node by an increment. So that increment is now plus 5. So this value becomes 28. Okay. And once going back from the left and right, what do? You see, okay, what is the minimum? So minimum still remains 21. And again, going back, you update your all the nodes in the parent tree. Okay. So in this case, while going back, those nodes will not be updated. So since it's like a post order traversal, so first the children will be updated and then the parent node will be updated. So I hope you understood this update, and let me give you one example in which you are doing a query. Okay, so let's see one example of a query. So now suppose you want to do a query in which you want to find out the minimum element in the range, let's say 0 to 1. Okay, so in the range 0 to 1, the element should be 21. Okay, so what do? You just traverse this tree and you basically reach this node, and from here you can see the minimum is actually 21, so that you can return back by the normal method. So this answer will be 21. And let's do one more thing. Let's do another query in which we will resolve a lazy value. Okay, so let's say the query is from, let's say, 3 to 5. We want to find out the minimum element in the range 3 to 5. So that element should be 4. So what do? You start traversing the tree. Okay, once you go right, you will find there is no overlap, but once you come on the left, you find there is an overlap. So at 3 to 5, okay, we missed out something. Right. So when we applied this update, 0 to 4, the increment should have been done by plus 10. So yes, so this will be also updated as plus 5. So this element should be plus 5. Okay, because if you take the minimum from the left and if you take the minimum from right, it should be 5. Oh, it should be 4, right? So the minimum should be 4 at this particular point. Yes. Okay, so you have a query from 3 to 5, and now you can see how we can perform this query. So at this node, this is 4, right? So at this node, you can see there is a complete overlap and there is no lazy value. So you directly return the answer from this node. So it will be still 4. But suppose you want to find out the value of the element at the third index. Okay, so the value of the element at third index. So let's say there is a query 3, 3, and you can see currently the value is -5, but there is a lazy value of plus 10. So you traverse down the path to this node. Once you reach this node, what do? You see this node carries a lazy value of plus 10. So that means that nodes need to be resolved. So you first resolve it and then you return the value. So resolving means you make the lazy value as 0 and you update the node value as plus 5 from -5. So this value you will get as 5, and you can see this value is 5. Okay, so you can get a mix of updates. You can have update query, update query, and so on. So this is how lazy propagation works, and in the next part we will see the implementation. Hi everyone, so now we will build lazy segment tree code. So in the first part we will build the update range lazy function that will update elements in a range L to R, okay, given what value you need to increment, and rest of the parameters are same, okay. And there is one change. Apart from the regular array, we also need to take another array that is a lazy array, and you can see I have constructed a large array and all the elements have been initialized with 0. So that means lazy of every node in the beginning is actually 0. So the build tree code will remain same, no changes in that. And here we have called the build tree function that will initialize the initial tree that we need to have from the array. Okay, so you're given an array, you build a tree, and after that you start performing updates on that tree. So let's see how we can build this. Okay, so in this function you are actually doing a tree traversal. Okay, in tree traversal what you do, you basically start from top and you try to um, traverse the tree in a top down direction, and then you come from bottom to top towards the root node. Okay, so one thing that you need to note is, once you are, let's say, going from any node to the left or right, and if this node has a lazy value, you need to adjust that lazy value and propagate it down to the children node. Okay, so for example, if this node is 5 and it has a lazy value of plus 10, what you will do, you will say, okay, I will pass on the lazy value to the left, I will pass on the lazy value to the right, and I will make this element as 15, and I will make this lazy value as 0. So this is what is the meaning of resolving the lazy value. So that's what we are going to do in the first step. So before going down, resolve the lazy value if it is there in the current node. Okay, so if it exists, so if lazy of index, so current node is index, if this is not 0, then resolve it. Okay, so resolving is very easy. So what you do, you say tree of index plus equals to lazy of node. So you update the current node, and if it is not a leaf node, so how do you check? For a non-leaf node, you pass on the lazy value to the children. So if ss is not equal to se, that means it's a non-leaf node, then you pass on the lazy value to the left child. So lazy of 2 into index plus equals lazy of index. So lazy value of parent is passed to the lazy value to the right, left and the right child. So that's 2 into index plus 1 plus equals to lazy of index. And you can see I'm not making any recursive calls here, we are just updating the value at the current node and just passing that value to the left and the right child, and this is clear the lazy value at the current node. Okay, so this is the first step. Okay, now we will think of the base case that we can reach. So now suppose you are updating a range, let's say from 0 to 2, but, or let's say you are updating a range from 3 to 5, but somehow you pass this query to this node. Okay, you pass this query to this node which contains the answer from the element 0 to 2. So in that case there is a case of no overlap, so you will go back from this node. So what we can do is, if ss is greater than r or l is greater than se, we can actually return. So let me draw this case. So we have node range from ss to sc, and we have query range from l to r. So you can say if r is greater than if ss is greater than r in such a case. Okay, or you have a case in which l is greater than se, then also there is a case of no overlap and we will just return. So that's a case of no overlap. Now we will have the recursive case. Okay, and there will be actually two types of cases because we are using lazy propagation. Not exactly two cases, basically there will be a recursive case. Okay, so let's see in the recursive case what we need to do. In the recursive case, suppose you come to a node. Okay, you come to a node, let's see, you are doing a query from, let's say, 0 to 2, and you come to a node which contains the answer for this query 0 to 2. So we have already discussed in such a case what we need to do. we need to stop at this point. Let's say the update is plus of increment, so you update this node by this factor plus of increment, and you pass a lazy value to the left child and to the right child without making a recursive call on the left child and on the right child. Okay, and we will actually return from this node. So this is the optimization part. Okay, so there will be actually two cases. So in one case we have to just do updates at the current node without making recursive calls on the left part and on the right part. So this will be another case. So if SS is greater than equal to L and SA is less than equal to R, so it's a kind of a complete overlap case. Okay, I will explain you what we are doing here. So we have to set tree of index, increment your current node by this increment, and create a new lazy value for the children node. Okay, create a new lazy value for children node. So that means if SS is not equal to SC, if children exist, it's a non-leaf node, then lazy of 2 into index should be equal to increment. Now you can see this is not a past value, this is actually a new value that we are creating, and lazy of 2 into index plus 1 should be incremented by increment. Okay, and we can return from this point. So this return statement is actually quite important. Okay, so that's the case of a complete overlap. So let us see again. So suppose your range is like say, so let's say um, the query is to update all the elements in the range, let's say 0 to 5, but somehow you reach a range in which you are at a node 2 to 4 and you want to update all the elements. Okay, let's say it's let's say 0 to 4. Now you can see 2 to 4 completely lies in this particular range. Okay, so that means we have to update all the elements that lie in this node, okay, and in the subtree of this node. So let's say what we do, let's say there was a lazy value x here, there was a lazy value y here, and we say okay, we want to update this node by an increment. So we say okay, this value was v, so we make it as v plus increment. So that's what we do. And we say if this is not a leaf node, we increment the lazy value of its children by a factor of increment. So this lazy value was x initially, so x can be 0, so it becomes x plus increment, and if this lazy value was y, it becomes y plus increment. So that's what we do, and we actually return the value from this particular node without making a recursive call on the left and without making a recursive call on the right. Now comes the recursive case in which you kind of have a partial overlap. Okay, so in that case you need to call both on the left and both on the right. So for that we need to find out the midpoint, that is SS plus SE by 2, and then we need to call update range lazy function. We need to give tree SS mid L to R increment, and the left child is 2 into index, and update range lazy tree mid plus 1 SE L to R increment 2 into index plus 1. That's it. And we also need to update the current node. Okay, that's like a build function. You know the answer from the left, you know the answer from the right, so update the tree of index. So that tree of index, it's going to be minimum of tree of 2 into index comma tree of 2 into index plus 1, and you can say return. That's it. Oh sorry, this index should be index. Okay, so this function is now complete. Okay, so let me just quickly explain you the third case. So here we are saying okay, suppose your range is from let's say 3 to 5, and you are at a node in which you have 0 to 5. Okay, so what you do, you make a call on the left and you make a call on the right. Mm, okay, so some of you may get confused. Is it a case of a complete overlap? The answer is no. So this is SS, this is SE. So your node range is 0 to 5. That does not completely lie in the query range. So it's a case of a partial overlap. Okay, so what you do, you make a call on the left, you make a call on the right, and here you see it's from 0 to 2, and here it is from, let's say, 3 to 5. So from here you will return, and your updates will be processed at this particular node, and the lazy value will be propagated to the left and right. Okay, so something like this you are going to do. So this is the case in which we will make a call on the left and we will make a call on the right. So I hope update lazy is clear, and now we will write the query lazy function in the next part. Hi everyone, so now we will write the code for the query lazy function, and this will be a little simpler than the update lazy function, because in update lazy there were two cases. You have to create new lazy values and you have to resolve old lazy values while going down. So we will not have something like this because it's caused due to a new update. Okay, and these are the lazy values that need to be adjusted because of the previous updates, and we needed to resolve them. So update function will be query function will be little simpler. So let's build it step by step, and I will explain you what we need to do. So function is int query lazy, and let's give the tree and other parameters. So query starts from QS, query ends at QE, and we get the index of the node at which we are currently at. Okay, so first step will remain same. Okay, so if you're coming to a node and that node has a lazy value, you need to resolve it. So that's the first step, and that will remain same. So you need to resolve the lazy value at current node. Okay, so this logic will remain same. So I just copy it from here and I will paste it here. Okay, now starts our main query logic. Okay, so let's think of some base cases. Okay, so in base case there could be a possibility that there is a case of no overlap. Okay, so that's the simplest possible case. So if SS is greater than QE or SE is less than QX, and what we need to return in this case, for example, uh, let's say you're querying for the range, let's say 3 to 4, but you're standing at a node 0 to 2 and you want the minimum from this node. So it what should it return? So it should return int max. Okay, so whatever is the value. So since there is no overlap here, so in case of a range minimum query problem, we will return the maximum possible value. That's going to be return int max. That's it. And another case would be a case of a complete overlap, in which means you already found the answer. Okay, so complete overlap. So you can say if SS is greater than equal to QS and SC is less than equal to QE, then you return the answer from this particular node, return tree of index. Now an interesting thing to note here is we are not checking lazy values at this particular node. Can you guess the reason why? The reason is very simple. If you're coming to this case, that means you have already resolved the lazy value at that node by writing this piece of code. Okay, and there is no return statement in this code, so that means this is like a code that will execute for every case. Okay, so that means if you are let's say doing a query at this particular node, there is a lazy value, let's say plus 10 here, and suppose you want the answer at this particular node, let's say this answer is 1, this answer is 2, this answer is 3. So what will happen? You start reversing, you come here, you come here, and at this point you see, okay, I want the answer for this node. Let's say this index is, let's say, 0, 0 comma 0. So what happens in such a case is, once you come down, so this lazy value is 0, so it gets adjusted. Once you reach this node, this lazy value gets adjusted, it becomes 12, it becomes 0, and once you come down, it gets a lazy value of plus 10, but If you come to this node, this lazy value gets adjusted and it becomes 13. Okay, and once you know there is a case of a complete overlap, that means your uh, query range is big. Let's say it's from 0 to 4, but you want the answer from the range 2 to 3. So the node range completely lies inside the query range, so you return the answer for this particular range. Okay, so that's given by tree of index. So this is QS, this is QE, this is SS, and this is SE, and you can verify. It's pretty logical as well, right? Otherwise, there would be a case of a partial overlap in which we need to call on both the sides. So we need to find out the midpoint. So that's going to be SS plus SE by 2. And also you can note in this case there was a change in the update function because we had to actually create a new lazy value. Okay, so this is the change because we were doing a new update by a factor of increment, so that leads to creation of new lazy values for the children of that particular node. But there won't be a case like here because we are just doing a query, and while doing query we just need to resolve the lazy values which we are doing on the top. Okay, so let's write the final case. We need an answer from the left that will be given by query lazy, and this will be tree SS mid QS QE 2 into index, and we want the answer from the right, that will be query lazy tree mid plus 1 SC yes, SC QS QE and 2 into index plus 1, and here we can return minimum of left and right, so that's going to be left and right. So that's it, and now we can just take some inputs and test our code. Okay, so let's see this example. We have this array 1 3 2 minus 5 6 and 4. So we first apply an update u1 in which elements from the range 0 to 2 get updated by value 10. So it becomes 11 13 12 and minus 5 6 and 4. Then we apply another update in which elements in the range 0 to 4 they get incremented by 10. Okay, so all these elements, so it will be 21 23 22 5 16 and it will be 4. Then we do a query. Okay, so you can see it's a mix of updates and queries, and we say okay, I need the first element, so that element is 23, so we should get an first answer as 23, so that's the answer for query 1 for the range 1 to 1. And then we will apply another update. We say okay, update all elements in the range 3 to 4. Okay, so that is this range, and sorry 3 to 5, yes 3 to 4 and incremented by 10. So these two elements will be incremented, and let's say it becomes 15 and it becomes 26 and it will be 4. And then I say okay, give me the minimum element in this particular range. So this element is going to be 4. So query 2 should give us the answer 4 for the range 3 to 5. So let's test it, and let me run this code. And you can see for query 1 we are getting 23, and for query 2 we are getting 4 as the answer, which means this is correct. Okay, so both our functions are working fine, and I hope you now understand lazy propagation in segment. Hi everyone, so now let's discuss the range sum query problem in case if you want to apply lazy propagation in such a case. Okay, so we have queries and we have also updates. So I will just discuss what lazy value will be stored and how it will be resolved. So let's say you have an array like this, and let's say the elements are 3 1 2 6 4 8. So let's say there is a query which says okay, update the elements from L to R by a value of plus 10. So maybe let's say this index is 0 1 2 3 4 5. There is a node which stores, let's say, the answer from the range 2 to 4, and maybe okay, there is a bigger tree. I'm not going to draw the entire tree, but suppose you come to this node and you find okay, this is the node where I need to update my answer from I want to update all the elements and I want to make them as 13, 11 and 12. So what will happen in this case? So earlier, let's assume that you know that you need to update this by a value of 10. So what lazy value you will keep? So this lazy value will be just 10, but at this point, if you want to resolve this lazy value, okay, so let's say this old sum was 3 plus 2 5 plus 1 6. So what value you will add to your current sum? So that will basically depend upon, so if you see the sum of the updated array, so the problem that we are doing is sum query. So in the minimum case it was fine, you just add 10 and your work was done, but the problem is with sum, and if you update all the elements then the sum will increase by an amount of 10 into 3, that is the number of elements. Okay, so what you can do, you can just say that okay, if there is a lazy value that will be 10, so this lazy value will be propagated to the children, and if I want to resolve this lazy value at this particular node, or if I want to make an update to this particular node, so I will update it like this. I will say 6 plus 10 into 3. So this answer will be now 36. And although you may have this answer as, let's say, 3 plus 1 4, but this answer will not be updated as of now. So maybe later on when you need to update this value, so how you will update this value node, this answer, so it will be 4 plus 10 into 2, because this node is responsible for storing two elements, okay, maybe from 2 to 3, let's say. So it will be 40 plus 2 42, so something like this. Sorry, it should be 20 plus 2 22. Okay, so you can see that, sorry, this should be 20 plus 4, that is 24. Now you can see, if you just want to get these two sums and you reach this node, so if you resolve this value, so the node is storing 4, the lazy value is 10, and the range that it represents is, let's say, 2 to 3. So if you want to resolve this node, so what I am saying is, you will add 4 plus this thing, r minus l plus 1, that is the number of elements that this node represents, into the lazy value, that is 10. Okay, so this will give you 4 plus 3 minus 2 plus 1 into 10, that will be equal to 24. And you can see this is now the correct sum after update. So 13 plus 11 is 24, and also if you add 12, so this sum is 36. So basically I'm saying, when you are resolving the lazy values, depending upon the type of question, you have to make the required updates. Okay, so in that case we will write tree of index plus equals to whatever is the increment that we are doing, or whatever is the lazy value, multiplied by r minus l plus 1 into whatever is the increment that we are doing. So this is the update that you need to apply while pushing your updates, and you have to take care of this term. Okay, that's it for this video, and I hope you will be now able to apply lazy propagation on range sum query example as well.
Yeah, so the topic for today is persistent segment trees. And now I'll first define what a persistent data structure actually is. So, starting from the term persistence, what does persistence actually mean? It means to retain. So, a persistent data structure is actually a data structure that retains all the modifications that take place on that data structure. So, starting with an example for a persistent data structure, I have a problem that I have taken from Anudeep's blog from persistent segment tree, for persistent segment trees, It's a very good blog and it's worth a read for persistent segment trees. So the question comes as follows. We are given a linked list and there are two types of operations that need to be done on that linked list. The first operation being that we can update some initial X values on that linked list and the second is that we need to print the linked list after some kth update. So the point here actually is that the kth update, how do we print the kth update? In this case, we cannot update the X values as they come in because, for example, if we have some linked list like this and now I update the first two values to some new numbers which is let's suppose 5, 6. So my new linked list looks like this. And now if I update the first three numbers to some new numbers that are 7, 8, 9 respectively, then this is how my new linked list looks. So the point is that if someone now asks me to print the linked list after the first update, so actually I have to print this entire linked list. So this is how a persistent data structure works. It doesn't keep the updates in place. It actually does an update and then we can retrieve any update because it retains all the updates that are done on that data structure. So now how to optimize the usage of a persistent data structure, that's the question for the day. Because if we construct a new linked list every time, then let's suppose we have n updates on that linked list of size n. So can you guess the complexity of this whole thing? Yeah, so the complexity would be O of n into n, because each time we are constructing the entire linked list which is of size order n, and we are doing this for n times, so this makes the complexity to be O of n square, which is not what we prefer. We can do something better. So I'd recommend that you pause the video and think of a solution to this problem. Yeah, so how to approach this? So the first step would be, let's assume we have 1, 2, 3 and 4. Now an update comes that says us that we need to update the first two values that are 1 and 2 to 5 and 6 respectively. So since we know that the other two elements of the linked list would remain the same, so for example I get an update of so I'll do it like 5 and 6, and now since these are two elements, I'll attach it to the third element in the previous linked list, and this gives me a reduction because I do not need to create the entire linked list again. Now jumping on to the next thing, how if I get an element update, a 3 element update which is 7, 8, 9, then what I need to do is that I'll go I'll write 7, 8, 9. And now, where do I need to point the 9? The 9 would point to the fourth element of the previous linked list. So, it will actually point over here. So I guess now I have made it clear how to apply this to the entire thing. Yeah. So this is how the updates will actually work. And now the entire thing would be that if we have an X element update, then we'll actually attach the new linked list of X elements. Let me clear the board. Yeah. So I'll attach the new linked list of X elements in front of the X plus 1th element of the previous linked list. Yeah. So basically, the X plus 1th element of the previous linked list would be the next element to the first X elements of the new linked list that's coming in. And this is how there would be a reduction in the space as well as the time. So now you have some time to guess what would be the complexity in terms of time and space for the new algorithm or for the new solution that we have. So it would be O of n plus x1 plus x2 and so on up till xm, where x1, x2 are the sizes of the element updates that are taking place, and this is the space complexity as well as the time complexity. Yeah. So this is a persistent data structure in the form of a linked list, and as we can see, we can actually keep all the updates that are taking place on the linked list as they are. So we can print the linked list after the first update, even after the second update, even after the third update, and maintaining the space and time complexity to be this. However, the main thing to note over here is, even if if all these X elements, X element updates are of order n, then our complexity would actually land up over here. But in the case where these element updates are actually close to order n, then our space and time complexity reduced to O of n, which would have stayed O of n square in that case. So now we'll be jumping on to the important topic of the day, which is persistent segment trees. So coming on to the topic, persistent segment trees. So as we have got the clear idea of what persistence in data structure actually means, now we can easily understand what persistent segment trees would actually function like. So a persistent segment tree would actually keep all the updates that are taken place on that segment tree persistent, or we can say it that it will retain all the updates that are taking place. So let's assume that we have a segment tree, and as we all know that the segment tree has a divide and conquer strategy. So it looks something like this. Let's assume that we do a point update in some place on this segment tree. Like if I have a 4 element segment tree, then this would be one. These both would be two-sized nodes of the segment tree, and these all will be one-sized nodes of the segment tree. Yeah. So like if we have an update, let's assume these were 1, 2, 3, 4, and it was a max segment tree. So the value that would be stored over here is 2. The value here that would be stored over here is 4, and the value which would be stored over here is 4. So this is a max segment tree on this array 1, 2, 3, 4, which looks perfectly fine. Now if I want to update some element, let's assume that I need to make this one to be 5. So can you tell me how many nodes in the segment tree would actually change? So it's very clearly evident what are the maximum number of nodes that can change on a point update. So now the segment tree would look like 5, 5, 5, 2, this is the same, 4, 3, 4. So actually we can see that there is change only along the ancestors of this particular node on which the point update has actually taken place. That's the catch. So it gives us a login update. So basically we have login number of nodes that are actually updated. Because login is actually the size, or maybe I can say it order of login, and yeah, so login is actually the height of the segment tree. So yeah, this is the whole thing. So what better I can do to store all these updates? Like this is one update, so I don't need to store the entire segment tree as it is all over again. So what I can do is I can just keep some of the nodes to be the same and the others ones to be pointing towards the previous segment tree and removing this extra memory that is being required. So now we are just keeping 3 elements which are newly added. So this is how the segment trees function, the persistent segment trees function. They keep the pointers to the entire portion of the segment tree which was being used earlier, so that we do not create it repeatedly. And therefore in persistent segment trees we have O of login time as well as the space complexity for each update. So we can now very easily print the segment tree after the first update, which is this. And for each update, we just need login information for that particular update. So this is the entire theory thing for persistent segment trees. Now we'll jump on to a question, and after that we'll see how we can actually implement persistent segment trees. The coding part would mostly be based something on pointers, because we need to use the portion of segment trees which were previously built for the new segment tree, so that each update isn't costly in terms of time and space complexity. If you have any doubts on this, you can go and read the Anudeep's blog on I don't remember actually. You can just Google search it, Anudeep's blog on persistent segment trees, and you can give it a read. I myself gave it a read when I was not able to get what persistent segment trees actually are. Yeah. So now let's come on to a question based on persistent segment trees. So the question is COT on Spotch. It's named count on a tree, I guess. So the question goes as follows. The question states that we have a tree consisting of n nodes. You can obviously read the question from the site as well. The link to the question will be below this video. And yeah, so the question is that we have a tree consisting of n nodes, which are numbered from 1 to n. Each node actually has an integer weight. Here, not the edges. Instead, a node has a weight. So each node has a weight which can be any integer from minus 10 to the power 9 to plus 10 to the power 9, basically in the int range. So what you need to do is you need to print the kth integer or the kth integer weight from when you are traveling from one node to other node. So basically the query would be in this form: u, v and x, or basically k. So we need to print the kth element in the sorted order when running from node u to node v, or I can more clearly show it to you. So let's assume that this is our tree. This is node number 1, 2, 3, 4, 5, 6, 7. And let's assume this node has some weight 2, this has 1, this has 10, and this has 6. So, and some random weights to these as well. Let there be 6, 8, 9. Yeah. So, you need to, so for a query can be like 4, 3, 2. So, 4, 3, 2 means that on the path from the node 4 to node 3, we need to print the second element in the sorted order. So what that means is, first of all, we need to see all the elements that are present on the path from 4 to 3. The elements are 2, 1, 10 and 6. So we need to sort them first. The sorted order would be 1, 2, 6 and 10. And now the second element in this is 2. So the answer to this query would be 2. It's as simple as that. So This is the entire question. Uh, Obviously, we don't need the brute force way. The brute force way is very simple. We just need to compute the LCA of the two nodes. Then we can run from this node to the LCA and from this node to the LCA again and put all the elements that come on our way. And once we are done, we just need to sort them and print the element that is on the kth position. But obviously this is not the required way because this is just a brute force approach to solve the question. So you can think of a solution using persistent segment trees as I described above before. So basically getting onto the solution is quite tough initially because you need to know how persistent segment trees can be used on trees. So actually this is a tree. Yeah. So I hope the question is clear. If it isn't, then you can see it on Spotch. It's named COT. So yeah, let's start. The solution would be something using persistent segment trees only, and this would how the solution will go. So first of all, what we need to do is we need to find the LCA. Yeah, so the first part would be finding the LCA for the two nodes U and V which I get. Let the LCA be L. Yeah, so this is a step which in which you can use a login approach, which would be shown to you in the LCA video, the lowest common ancestor video, wherein we can find the lowest common ancestor of two nodes in a tree in log n time complexity. Yeah. So the second step would be coordinate compression. Even if you are not getting things right now, you can just go through the video and you'll get it eventually. So the coordinate compression, as you may or may not know, it is something like reducing the values to a specific range. For example, let's assume I have some values ranging from minus 10 to the power 9 to 10 to the power 9. But there can be only at max 10 to the power 5 values, which is actually the case for our weights. The weights can range anywhere between these, but there can be only these many distinct values, let's assume, because there are only at max these nodes in the tree. So in this case, we can actually compress these values to some other values so that we can work on a segment tree. So the values like 1, 3 and 5, let's assume, can be mapped to 0, 1 and 2. And let's assume we have some 10 to the power 9 as well. So this can be mapped to 3. So in this case, we can very easily see that the person who is bigger stays bigger here as well, which is the property which we need to maintain over here. So I guess this is clear. The next step is actually finding out the solution to the problem. So one thing that could come to anyone's mind would be something like a binary search. But binary search on what? Yeah, so a binary search can be something like this. So let's assume that I have all the elements from node 4 to node 3, or maybe from node U to node V. So I need to create some function f which gives me the number of elements that are less than or equal to x maybe. This can be described as the number of elements less than equal to x from node u to the root of the tree. Yeah, now things make sense. So the same function f for v would be the number of elements less than equal to x from node v to the root of the tree, minus f of LCA of u comma v x. This is actually the number of elements less than equal to x from the LCA of the two nodes to the root of the tree, minus So hopefully I'm making things clear over here. If this thing is not visible to you, then I can write it again. Then so this thing may be a problem for some people. I'll explain it to you. So actually, let's assume I had to find the number of like all the elements from 4 to 5 range in the path from 4 to 5, from the node 4 to node 5. Yeah, so I can include all the elements that are from 4 to the root of the tree, which is 1. So this I'll consider 2, 1 and 10, and then I can again consider all the elements from the node 5 to the root of the tree, which is 6, 1 and 10. Yeah, and now I need to subtract all the elements that are from the LCA of the nodes 4 and 5 to the root of the tree, which is 1, 10. And now if I write f of LCA UVX again over here, then actually I'll remove this 1 again, which is not the desired case. So I need to remove the 10. So what happens over here is this 10 gets cancelled from this 10, this 10 gets cancelled from this 10, and one of the ones gets cancelled because we cannot consider the LCA element twice. So this eventually leaves us with 3 elements, which are 2, 1 and 6. So this is how this entire thing goes. So if we have some function f which can do this for us, then we just need to binary search. We need to binary search for all the x values, and since the x values have been compressed now, so I need to binary search for all the x values in the range 0 to n minus 1, where n is the number of distinct values. And this gives me the solution. But I need to binary search for this function, binary search on this function. So I need to figure out what this function could be that helps me in the binary search. So that function would come from the concept of persistent segment trees. Finally, I'll keep the question intact and this f function intact over here. So now let's assume that we have a segment tree. We have a segment tree at every node which can help us compute the f function. How simple that would make the things to be, right? So what that segment tree would actually store. So first of all, like in this case, we have the different values to be 1, 2, 6, 6, 8, 9, 10. Since I'm considering the distinct values, I can remove this. And I can actually perform a coordinate compression over here. So 1 would map to 0, 2 would map to 1, 6 would map to 2, 8 to 3, 9 to 4, and 10 to 5. And now we'll go onto this tree. So if we are to maintain a segment tree at each node, so how that segment tree would look like is as follows. So since I have 6 distinct values ranging from 0 to 5, so and the first node contains a 1 over a 10 value which is mapped onto 5, so I'll mark a 1 over here. This is the array on which the segment tree up till this root node would be constructed. How would the array for node number 2 look like? You can pause the video and think of it. The value would, now it has a value 1 which is mapped onto 0, so it would look like something like this. The 1 here stays the same because it has to contain all the elements which are there in its ancestor and then add its contribution to it. So now I'll jump on to 2. How the array for the element number 2 would look like, on which the segment tree for that particular element will be built. This is node number 4 and the value is 2. 2 is mapped onto 1. So it will look something like this. Similarly, I can make it for 6. 6 has been mapped onto 2. So 0, 1, 2, 3, 4, 5. And now it looks like 1, 0, 1, 0, 0, 1. And similarly, you can construct it for others as well. So how would these segment trees help us is that if I can compute this f function on these segment trees very easily. So let's assume that x in my case is 4 right now. So f of ux is basically the sum of elements up till here. So this function, when binary searched, can give me the answer. So this function entirely should give me a value less than equal to k, or basically if I want the kth element, then this entire thing should be equal to k, I guess. Yes. So for the point where this value becomes equal to k, considering that x gives me the elements less than equal to x, then I can not be entirely sure, because it may happen that there is a 0 at the position of x. So instead, I should change this function to be number of elements less than x. But still there can be an issue, so keeping it to be equal only, because in any way if we are having a 0 over here, then that can cause an issue, because we cannot be sure whether this element is actually there or not. But the point I'm trying to make over here is that we can very easily find by doing it with a binary search perspective. Yeah, so the point where this whole sum, considering this to be a prefix sum, which obviously it would be, so where this the first place where this prefix sum actually exceeds k is the point where my answer lies. So that is the point where I'll get the kth update. So I need to find first point where this is a prefix sum, because I'm considering all the elements which are less than equal to x. So it's giving me the count. So it's actually a prefix sum, considering I'm marking the frequencies over here for each of them. These are actually the frequencies. So if I get 6 below a 6, then this then in the child of that parent, I'll update the value to be 2, means 1 for that 6 and 1 for that 6. So these are actually the frequencies. Yeah. So the first point where this sum becomes greater than equal to k is the point where I have the solution. But this can be done by a binary search. But the catch over here is that we are building a segment tree at each node. So eventually this will give us a segment tree of O n size over here, O n size over here, and this will eventually give us the complexity to be O of n square in terms of size. And the space would be a completely the time would be a completely different thing, because considering the time would be quite fine with this. Yeah, but the time would still stay out to be m into log n square, where m is the number of queries we have. 1 log n in here comes from the binary search, and 1 log n from in here comes from the segment tree part, the point where we are finding this function in the segment tree. But the point is, we need to first of all reduce this thing, and then we'll come over here. So I need to somehow reduce it to n log n and not n square. And this is where the strategy which I explained to you in the beginning will help us. Since I know the segment tree for this there's only one update that the child of a parent brings into its segment tree. So that's where I just need a log n nodes for that particular child in extra to the nodes of the parent. So the other nodes that aren't changed actually point to the nodes of the parent, and the nodes which are changed are actually created for the child again. So this is how there's a log n extra space required for the child in comparison to the parent, and this would happen eventually throughout the tree. So each child would add log n nodes. So eventually the space would be order n log n, which is our required space complexity. Hopefully I'm making things clear now. So yeah, this is how the structure would look like. And now we can see the implementation details when I write the code for it. The code would most likely be a different video, but till the time you are getting the objective of this, then it's fine. So this is how the things would be over here. So now we have reduced the space complexity. So it will actually function the same as the n segment trees would have functioned, but we have done this in O of n log n space by adding only the updated nodes and not the entire tree. Just the pointer way, which I explained earlier. Now the space has been reduced to O of n log n. Great. But do we actually need a binary search over here? So actually the time over here is log n into log n, which comes from the binary search part. I somehow want to reduce this binary search part in this. So how can we do things better? So now I'll jump onto the solution to this, wherein we'll be going on to a complexity which is like this, which includes the n log n for the construction of the segment tree and log n for answering each query. And since there are m queries, the complexity would look something like this. Yeah. So now let's see. Cool. n plus m log n is the space complexity. It's the time complexity for our solution. I'll write it again, is the time complexity. This is the desired complexity, and it is the complexity in which we can easily solve it. So actually these are actually 4 segment trees which we are referring over here. Am I making things clear for you? Because each node has a segment tree. Now we can always consider in this case that each node has its own segment tree, even though it just has log n nodes because of the thing I told you earlier. So these are actually 4 segment trees. 4 segment trees. These so the 4 segment trees are of the node U, the node V, the LCA of node U and V, and the parent of the LCA of U and V. Yeah. So these are the 4 nodes, the 4 segment trees which are into our consideration. So these would give rise to a new segment tree, which we can think in our perspective is a new segment tree, because actually they are updating values on the same array. So not exactly the same array, I will say, but yeah, they all have the same range on which they are working, which is from 0 to n minus 1. So I can consider that I have formed a new segment tree which actually works as follows, which is actually the sum of these 2 segment trees minus these 2 segment trees. So this is how our new segment tree would look like, and it would be constructed from the 4 segment trees that I have already explained to you. But the point is this consideration correct? Absolutely, because if I consider this, what this stores is all the nodes, it stores the frequency of everyone that's present from U to the root. This stores the frequency of everyone's that present from V to X, and so on and so forth. Same for this and same for this. So the new segment tree would actually just be a combination of all of these working on the same set of elements. So when the left of the new so the root of the new segment tree would actually be the sum of the values of the roots at these minus these values. And what would be the left child of the new segment tree? I need to go left over here, and subtract the left from here and subtract the left from here. So this is how actually things work. So the left of this segment tree is actually going left into this, and adding the values left of the left element of the left child of the root in this, and subtracting the values of the subsequent elements, subsequent nodes in these segment trees. So this may be a complex thing initially, but once you realize that these 4 segment trees will actually eventually lead to the formation of a new segment tree, which can be thought of as a virtual segment tree, then the things would be very easy for you. So now if I need to find the kth element, if I know that in the new segment tree I have 10 elements in total, wherein 6 elements lie over here and 4 elements lie over here, I need to find out the 8th element. So in my case, k is equal to 8. So I'm pretty sure that the k cannot lie over here. K will surely, the kth element would surely lie over here. So on this node, I'll subtract 6 from 8, and which will give me 2. So I need to find out the second element in this remaining part of the segment tree. And now let's suppose I have 3 elements over here and 1 element over here. Then I'm pretty sure that the kth element lies over here. And now if I have 1 element over here and 2 elements over here, then I know that 2 minus 1, the first element here which has a value 1, means which has a value greater than equal to 1, is the person that is the answer to my kth element query. And now if it has a 1-1 structure, then I know that it is this person. These are actually the frequency sums of all the elements that are present in that. So this means that there are 10 elements in total that are present, not necessarily distinct. Some elements can have values 2 of their frequencies, and some can have values 1, 3, 4, anything. So I now know that this is the person that I was searching for, and the position at which this number lies. Let's assume that this person lies at the position 8, sorry, 4. Let's assume. So in the coordinate compression which we did, I just need to store the reverse maps as well. So in this case, if 6, 8, yeah. So I know that if this is 4, then actually 9 is the number I was searching for. So this is how the entire structure looks like. And now I very easily know that I don't need to do this entire binary search thing over here, because this is actually a part of binary search. This is actually binary searching for the kth element, because in the log n size structure, but the log n here, instead of being multiplied, which was happening over there, is being added. So the complexity stays order of log n. The main thing over here, the gist is that you realize that these 4 segment tree summation would give me a new segment tree, and that would make things very clear for you. So this is the entire thing I wanted to explain. If I can make the idea for the new segment tree clearer to you, then I guess things would be more clear. So I just construct random 4 trees, one for node u. Segment trees would actually be working made on arrays. So like if I have something like this, then it may happen that something like this isn't possible, because I am assuming some things like I'm not taking into consideration that someone is the LC of other. I just need to make things clearer to you. So yeah, 1 0 0 0 0 1 and something like this, 0 1 2 3 4 5 0 1 2 3 4 5. Cool. And again I have so the new segment tree would actually, the point over here is that a segment tree is always, or in this case, is made on an array. So this will actually give me a new array. Yeah, so this is a very good thing to realize over here. So the segment tree is actually built on an array, and these 4 people will actually give me a new array. So like I'll consider this as 0 1 1 0 0. So actually I'll sum. The values over here would be summed and these would be subtracted. So array addition would be just adding the elements, subsequent elements that are present on a position. So if like I have 4 elements that are 4 arrays that are of equal sizes, then adding arrays is actually so the new array of I would actually be old 1 I plus old 2I. So if I were to add 2 arrays to form a new array, then I need to perform this for all I. For all I, new array of I is equal to old is equal to the position at old 1 and the value at old 1 at that position and the value at old 2 at that same position. So this is how things work. So here also I have a segment tree. Here I have an array. So subsequently I'll add zeros and again zeros, then 1 0 all zeros, then 4 would be 0 0 0 0, yeah, and 5 would actually be 1 1 1 1, so it would be 0. 3 would actually be 0 actually, yeah. So this is how the array would look like. So the segment tree is built on this array, and therefore now you can very easily realize that these 4 segment trees would actually give rise to a new segment tree, and this new segment tree would be the basis for my construction. And now the sum of all of these elements is what is stored in the segment tree. So this is a frequency segment tree. Finally, I'll construct a frequency segment tree from this whole thing, and hence I'll be able to solve the question very easily. Now, jumping on to the next problem. Hope I have made the things very clear in this problem. Things would be clearer when we'll implement this. I'll jump on to some other question, and you just need to think of a solution to it. We'll implement all of these later on. So the next question is named mkth num on spoj itself. So the question states that you are given an array again, and you are given queries like I, j, k, wherein you need to find the kth element from position I to j in a sorted order, just like it was given before. So let's assume like I have 2, 1, 3, 6, and I need to find out the 0, 1, 2, 3. So if my query is like I need to find out the third element from 1 to 4, then it will be 1, 2, 3, 6, and my answer would be 3. So it's almost similar to the previous question, but now I have got an array instead of the tree. How would you solve this question? Can you relate this question to the previous question? It's best in competitive programming to relate a question to some other question, so that you are able to get or reach to a better solution for that particular question. And obviously if you have coded once for a particular question, then you know how to code it again, right? And this actually helps in competitive programming a lot. So you can take a pause and think of it. How I thought of this question was very simple, and after writing the code for that question, you just need to make one change and you have written the code for this question. So how is that possible? It's very easy. So if you can think of it, this is actually a tree again. The 0th node is connected to the first to the second to the third. These are all elements of the tree instead of an array, and this tree is a linear tree. The tree is linear, and now these are actually acting as integer weights to the nodes. Yeah. These act as integer weights, and so this question is again reduced to the COT question. And this is how I solved it. We'll be coding both of them. So any doubts which you are having right now would be cleared then. So that's all for this video. Thanks for watching.
एक सीक्वेंस गिवन है, एरे, एक एरे गिवन है. क्वेरी का मतलब क्या है? क्वेरी ऑफ एक्स वाई इज मैक्स ऑफ दिस. मतलब एक सम दिया आई से लेके जे तक का. तो अगर ये एक एरे है और यूजर ने क्वेरी किया इस पार्ट पे एक्स और वाई, तो इसका आंसर क्या है? एक मैक्सिमम सम इन दिस पार्ट. सो इट इज नथिंग बट मैक्सिमम सब एरे. आई और जे क्या दिया? आई और जे लाई कर रहे हैं एक्स और वाई के बीच में. आई और जे यहाँ पे कहीं पे लाई कर रहे हैं. इट इज बेसिकली मैक्सिमम सब एरे सम इन द रेंज एक्स टू वाई. मैक्सिमम ऑफ ऑल सब एरेज इन दिस रेंज, इन दिस सब एरे, सब एरे के अंदर सब एरे की बात हो रही है। एक्स से वाई ऑलरेडी एक सब एरे है, उसके अंदर मैक्सिमम सब एरे सम की बात हो रही है। ठीक है, जो हमने नॉर्मली केडेन्स एल्गोरिथम से किया था उसको अब हमें यहाँ पे कुछ और करना पड़ेगा। तो अब जरा थोड़ा सा दिमाग लगाओ कैसे होगा इसको। ठीक है, इस केस में गिवन है कि 3 एलिमेंट्स हैं और वो एलिमेंट्स ये हैं। पहली क्वेरी एक ही क्वेरी है और 1 से 2 क्वेरी है। तो 1 से 2 क्वेरी करने का मतलब इतने पार्ट के अंदर मैक्सिमम सब एरे सम क्या होगा, 2 होगा। ठीक है, आई थिंक इंडेक्सिंग 1 से कर रखी है इन्होंने, इंडेक्सिंग इज फ्रॉम 1 या जो भी होगा 1 से 2 ये भी हो सकता है। हाँ, सो 1 से 2 यही है, इंडेक्सिंग 1 से हो रखी है। चलो देखते हैं एक एग्जांपल के साथ कैसे इसको हम अप्रोच कर सकते हैं। सो वी आर स्टार्टिंग। सो लेट अस से हमारे पास एक एरे गिवन है। एरे में जो एलिमेंट्स हैं वो 1 3 लेट से -4 5 -2 ये एलिमेंट्स हैं। एंड यूजर ने कुछ क्वेरी किया है, यूजर ने क्वेरी किया है, एक एलिमेंट और डाल देते हैं यहाँ पे, चलो इतने रखते हैं। ठीक है, सो हम इतने ही एलिमेंट्स रख के चल रहे हैं। अब बात यह कि 0 1 2 3 4, तो अगर मैं बोलूं मेरी ये रेंज है, ये 0 से 4 है, इसको ब्रेक डाउन किया हमने 0 से 2 में, फर्दर ब्रेक डाउन किया इसको हमने 3 से 4 में, ये हो जाएगी 0 से 1, ये हो जाएगी 2 3 4 0 और 1, राइट? ऐसा ही होगा। बात यह कि ब्रेकडाउन तो हम कर लेंगे, ट्री भी बिल्ड कर लेंगे, बट हर एक नोड में हम क्या रखने वाले हैं, व्हाट इज द वैल्यू वी आर गोइंग टू स्टोर इन एवरी नोड। तो देखो होने क्या वाला है कि अगर मान लो 2 एरेस कंबाइन हो रहे हैं, मान लो ये लेफ्ट पार्ट है और ये राइट पार्ट है। ठीक है, सो इनको जब मैं कंबाइन कर रहा हूँ, मर्ज कर रहा हूँ, तो ऐसा हो सकता है कि जो मैक्सिमम सब एरे हो वो कंप्लीटली लेफ्ट पार्ट के अंदर लाया कर रहा हो, दिस कुड बी ऑप्शन 1। या ऐसा हो सकता है वो कंप्लीटली राइट पार्ट के अंदर लाया कर रहा हो, दिस कुड बी ऑप्शन 2। या ऐसा हो सकता है कि उन दोनों को मर्ज करके एक एरे बन रहा हो, जब उन दोनों को मर्ज करें तो एक नया एरे ऐसे बन रहा हो जो यहाँ से मैक्सिमम है, और एक एरे यहाँ से बन रहा हो जो अपना मैक्सिमम है, राइट? सो ऐसा भी हो सकता है, दिस कुड बी ऑप्शन 3। ठीक है, सो इसको बनाने के लिए हमें क्या चाहिए, यहाँ से इस वाले पार्ट से मैक्सिमम सफिक्स सम चाहिए हमें लेफ्ट वाली साइड से। ठीक है, और राइट वाली साइड से हमें क्या चाहिए, मैक्सिमम प्रीफिक्स सम। इसके अंदर हमें क्या चाहिए, दिस इज द मैक्सिमम सब एरे सम एंड दिस इज द मैक्सिमम सब एरे सम फ्रॉम द लेफ्ट पार्ट। तो हमारा जो मैक्सिमम, ये L2R बोल देते हैं, जो भी L2R ये क्वेरी थी। सो आंसर ऑफ L2R क्या होगा, मैक्सिमम ऑफ दीज 3 ऑप्शंस, ऑप्शन 1 ऑप्शन 2 एंड ऑप्शन 3। अब मैक्सिमम प्रीफिक्स सम क्या होगा और मैक्सिमम सफिक्स सम क्या होगा ये निकाल के देख लेते हैं। ठीक है, सो अगर मैं इतने पार्ट की बात करूं तो प्रीफिक्स सम कितने 1, इतने पार्ट की बात करूं प्रीफिक्स सम हो गया 4, इतने पार्ट की बात करूं प्रीफिक्स सम ऑल्दो 0 हो रहा है, बट हमें तो मैक्सिमम देखना है ना, तो मैक्सिमम 4 ही रहेगा। यहाँ पे अगर बात करूं प्रीफिक्स सम कितना हो रहा है, 5 हो रहा है। यहां तक की बात करूं प्रीफिक्स सम कितना हो रहा है, 5 ही हो रहा है, राइट? सो दिस इज द मैक्सिमम प्रीफिक्स सम फॉर एवरी पोजीशन, यहाँ तक यहाँ तक यहाँ तक यहाँ तक यहाँ तक। अगर मैं चाहता हूं कि ये पार्ट मेरा एक लेफ्ट पार्ट है, तो या तो मैं यहाँ तक एलिमेंट्स लूं या यहाँ तक लूं, यहाँ तक लूं। ठीक है, यहाँ तक मतलब यहाँ तक कह रहे कि अगर बात होगी तो डेफिनेटली हम इस एलिमेंट को नहीं लेंगे, तो हमारा मैक्सिमम प्रीफिक्स सम 4 ही होगा कंसिडरिंग एलिमेंट्स अप टू दिस, इसलिए मैंने 4 लिखा है। ठीक है, ये बात समझ आ रही है? यहां तक अगर, सॉरी ये थोड़ा सा गलत कर दिया मैंने, राइट। इसको अगर लेता हूं, मतलब यहां तक का एरे अगर मैं कंसीडर करता हूं, तो वो सम कितना हो जाएगा, राइट। तो 4 प्लस ये हो जाएगा 1 प्लस 3 4 माइनस 4 0 प्लस 5 5। एंड यहां तक क्या, अगर मैं यहां तक कंसीडर करता हूं, मतलब इस रेंज तक की बात हो रही है, तो ठीक है, मेरे को पता है यहां तक लेना है, इस रेंज तक लेना है, तो इसका भी आंसर क्या हो जाएगा 5। तो किसी ने अगर तुम्हें बोला कि इतने एरे में बताओ कहां तक लोगे, तो ठीक है यहां तक लेंगे हम, 5 आ रहा है। ये बात समझ आ रही है प्रीफिक्स सम वाली? तो ये मैक्सिमम प्रीफिक्स सम है, मतलब अप टू मैक्सिमम उस इंडेक्स तक, राइट। सो दिस इज द प्रीफिक्स सम अप टू दैट इंडेक्स। सिमिलरली अगर उल्टी डायरेक्शन में निकालोगे तो सफिक्स सम निकाल सकते हो। सो अगर यहां तक एलिमेंट्स लोगे -2, यहां तक एलिमेंट्स लोगे -2 प्लस 5 3, यहां तक एलिमेंट्स लोगे तो -2 प्लस 5 3, -4 नहीं ले रहा। अब यहां तक अगर एलिमेंट्स लोगे या तो 3 होगा या फिर नया वाला जो सम बन रहा है। सो नए सम में क्या होगा, -2 प्लस 5 3 -4 -1 और ये 2, तो ये 3 ही होगा और यहाँ पे भी 3 होगा। इसको उल्टा सम कर रहा हूँ ना, क्यूमुलेटिव सम इन द रिवर्स डायरेक्शन, राइट। सो एक बार देखते हैं यहाँ पे, ठीक है। तो ये सम इस तरह से आ जाएगा, -2 और 3 3 3 आ जाएगा सबका, -2 3 3 3। ये मैं ऐसे ही बता रहा हूँ, कॉन्सेप्ट बता रहा था क्या है, ठीक है। अब देखो हर एक नोड पे हमें 4 वैल्यूज कंप्यूट करनी है, मतलब एक वैल्यू तो हमें देखो चाहिए। ये दो वैल्यूज तो समझ आ गई ना, मतलब जब एरेस कंबाइन होंगे तो राइट एरे का प्रीफिक्स सम, लेफ्ट एरे का सफिक्स सम, ऐसा सम जो सबसे ज्यादा है, ठीक है। सो हमें क्या क्या चाहिए, हमें चाहिए प्रीफिक्स सम PS, हमें चाहिए सफिक्स सम SS, और हमें प्रीफिक्स सम कैसे निकलेगा, देखो प्रीफिक्स सम निकलेगा जब मैं दो एरेस को कंबाइन कर रहा हूं। मान लो दो एरेस को मैंने कंबाइन किया, सॉरी इस तरह से कंबाइन किया, मतलब मैं दो एरेस को कंबाइन कर रहा हूं और मैं चाहता हूं कि मेरे को नए एरे का प्रीफिक्स सम पता हो, ठीक है। सो प्रीफिक्स सम या तो इसी एरे का प्रीफिक्स सम होगा, या फिर लेफ्ट एरे हम पूरा ले रहे होंगे और वो सब एरे राइट में कहीं पे टर्मिनेट हो रहा होगा। ये बात समझ आ रही है? यहां से लेके यहां तक या यहां से लेके यहां तक, दो ऑप्शन है। सो मैं क्या लिख सकता हूं, प्रीफिक्स सम इज नथिंग बट ऑप्शन 1 इज लेफ्ट का टोटल सम प्लस राइट पार्ट का प्रीफिक्स सम, या फिर लेफ्ट का प्रीफिक्स सम, इन दोनों का जो भी मैक्स होगा। दिस विल गिव यू द मैक्सिमम प्रीफिक्स सम फॉर द न्यू एरे। सफिक्स सम की बात कर लेते हैं। सफिक्स सम मतलब पीछे से सम, हम पीछे से सम करते हुए आ रहे, या तो राइट पार्ट का सफिक्स सम या फिर राइट पार्ट पूरा ले लो और वो यहाँ पे टर्मिनेट कर रहा हो। बेसिकली मेरे को नए एरे में निकालना है ना ऐसा सम जो पीछे से स्टार्ट हो रहा है और बीच में कहीं तक आते हुए मैक्सिमम हो रहा है, ठीक है। सो इट विल बी मैक्सिमम ऑफ राइट का टोटल सम प्लस लेफ्ट का सफिक्स सम, या फिर राइट का सफिक्स सम। अब क्योंकि यहाँ पे टोटल सम हो रहा है तो टोटल सम तो मेरे को कंप्यूट करना ही पड़ेगा। तो टोटल सम का फॉर्मूला क्या हो जाएगा, टोटल सम कैसे निकलेगा, लेफ्ट का टोटल सम प्लस राइट का टोटल सम। एंड प्रीफिक्स सम कैसे, अब मैक्सिमम सम तो एक्चुअली तो हमें मैक्सिमम सम कंप्यूट करना था। सो मैक्सिमम सम कैसे निकलेगा, तीन ऑप्शन थे, तीन ऑप्शन ये बनाए थे मैंने। पहला ऑप्शन क्या है, लेफ्ट का मैक्सिमम सम, मैक्सिमम सम इज नथिंग बट लेफ्ट का मैक्सिमम सम, राइट का मैक्सिमम सम, लेफ्ट का सफिक्स सम प्लस राइट का प्रीफिक्स सम और इसका मैक्स, ठीक है। तो ड्राई रन करते हैं इस चीज को अपने इस पे। तो देखो, अब अगर सिंगल ही नोड है, सिंगल नोड है अगर 0 0 0, तो चारों सम यही होंगे 1 1 1 1, प्रीफिक्स सफिक्स टोटल मैक्सिमम। अगली नोड पे 2 2 2 2, राइट। 2 वाली नोड पे 0 1 2 3 4, -4 -4 -4 -4। 3 वाली नोड पे 5 5 5 5। उसके बाद -2 -2 -2। जीरो से 1 का मतलब क्या है, ये दो एलिमेंट्स कंबाइन हो रहे हैं 1 से 2, तो इनका प्रीफिक्स हम क्या हो जाएगा, या तो लेफ्ट का टोटल प्लस राइट का प्रीफिक्स 3, या फिर लेफ्ट का प्रीफिक्स 1, तो मैक्स क्या है 3। सफिक्स क्या हो जाएगा, या तो राइट का सफिक्स या राइट का टोटल विच इज 2 प्लस लेफ्ट का सफिक्स विच इज 1, तो ये भी क्या हो जाएगा मैक्सिमम 3। तो इसका प्रीफिक्स 1 यहां तक देखोगे तो 3, सफिक्स 2 यहां तक देखोगे 3, तो मैक्सिमम सफिक्स हम 3 है, मैक्सिमम प्रीफिक्स हम भी 3 आ रहा है, ठीक है। टोटल सम लेफ्ट प्लस राइट 3, मैक्सिमम सम भी करोगे तो या तो वो होगा लेफ्ट का आपका मैक्सिमम सम 1, या राइट का मैक्सिमम सम 2, या फिर लेफ्ट का सफिक्स प्लस राइट का प्रीफिक्स। लेफ्ट का सफिक्स 1 है, राइट का प्रीफिक्स 2 है, तो ये क्या आ जाएगा 3, तीनों का मैक्स 3। 0 से 1 के लिए तीनों तरह के सम्स यही आ रहे हैं, ठीक है। 2 के लिए हमें आंसर पता है। अब 0 से 2 कंप्यूट करते हैं। 0 से 2 का मतलब एलिमेंट्स है 1 2 -4, 1 2 -4। अब देखो इसमें हमें बेसिकली एक पार्ट हमारे पास ये है और एक पार्ट ये है, ये दोनों पार्ट्स मर्ज हो रहे हैं, इनके आंसर हम निकाल चुके हैं, ठीक है। सो अब ये मर्ज हो रहे हैं, तो सबसे पहले प्रीफिक्स सम 1 3 3, फॉर्मूले से देखते हैं। फॉर्मूला ये लिखा हमने प्रीफिक्स सम का, लेफ्ट का ds प्लस राइट का प्रीफिक्स। सो लेफ्ट का टोटल कितना है 3, राइट का प्रीफिक्स -4, एक ऑप्शन ये है, या फिर लेफ्ट का प्रीफिक्स विच इज 3, दोनों का मैक्स 3। तो उसने बोला प्रीफिक्स सम 3 है, तो हमारा भी 3 आ रहा है, ठीक है। अब उसने बोला कि सफिक्स सम निकालो। अच्छा, सफिक्स सम देखो पीछे से शुरू करना है, सो या तो -4, या फिर -4 + 2 -2, या फिर -1, तो -1 आना चाहिए, मैक्सिमम तो -1 हुआ ना। सो ये कैसे निकलेगा, राइट का टोटल प्लस लेफ्ट का सफिक्स विच इज 3, सो -1, यही फॉर्मूला है ना। राइट का टोटल प्लस लेफ्ट का सफिक्स, या फिर राइट का सफिक्स सम। राइट का सफिक्स सम तो -3 है, -4 है, वो हमने छोड़ दिया, तो राइट का हमने टोटल ले लिया, तो सफिक्स सम आ गया -1। अब क्या चाहिए हमें, टोटल सम, तो टोटल सम होगा 3 -4 -1। अब हमें क्या चाहिए मैक्सिमम सम, तो मैक्सिमम सम होगा या तो टोटली सम लेफ्ट पार्ट में लाई कर रहा है, लेफ्ट पार्ट में मतलब इसमें लाई कर रहा है तो 3 आएगा, राइट पार्ट में लाई कर रहा है तो -4 आएगा, या फिर लेफ्ट और राइट को कंबाइन करके बन रहा है, तो उससे भी कितना आंसर आएगा, लेफ्ट का सफिक्स राइट का प्रीफिक्स, तो लेफ्ट का सफिक्स 3, राइट का प्रीफिक्स -4, तो ये भी आ रहा है -1, तीनों का मैक्स -1, तो इस सब एरे का मैक्सिमम सब एरे सम 3 होगा, तो ये क्या आ गया 3। ये चीज समझ आ रही है। 3 से 4 की बात हो रही है अब, 3 से 4, 3 से 4 में क्या एलिमेंट्स पड़े हैं 5 एंड -2। बेसिकली अब हम इन दोनों एलिमेंट्स को कंबाइन कर रहे हैं, 5 एंड -2 को, ये लेफ्ट पार्ट है राइट पार्ट है, और ये एरे बना रहे हैं 5 एंड -2 का, ठीक है। सो सबसे पहले हमें निकालना है प्रीफिक्स सम, तो प्रीफिक्स सम यहां तक लेते हो 5, यहां तक लेते हो 3, सो बेटर क्या है, सो लेफ्ट का प्रीफिक्स, प्रीफिक्स का फॉर्मूला देखो, लेफ्ट का टोटल प्लस राइट का प्रीफिक्स। लेफ्ट का टोटल कितना है 5, राइट का प्रीफिक्स कितना है -2, तो 3 आ रहा है, एक ऑप्शन हो गया 3, या फिर लेफ्ट का प्रीफिक्स विच इज 5, सो बढ़िया क्या 5। सफिक्स सम या तो -2 होगा या फिर हमारा 3 होगा। सो -2 और 3, सो कैसे आएगा, आ जाएगा, ठीक है। टोटल सम 5 - 2 3, मैक्सिमम सम 5। इतने पार्ट की अगर बात करूं तो मैक्सिमम सम लेफ्ट साइड का सफिक्स सम विच इज 5, सॉरी लेफ्ट का मैक्स सम 5, राइट का मैक्स -2, या फिर इन दोनों को मर्ज करके 3। सो 5 ही बेटर है, तो हमने इतना पार्ट ले लिया, तो ये सम क्या आ गया 5। अब तुम ये देखो, इधर से 5 इंक्लूड हो रहा है, बट जब हम अब इस पार्ट को ऐसे ब्रेक डाउन किया हमने, इस पार्ट का मैक्सिमम सम 5 है, इस पार्ट का मैक्सिमम सम 3 है, बट क्या पूरे पार्ट का मैक्सिमम सम 8 होगा? क्या पूरे पार्ट का मैक्सिमम सम 8 होगा या नहीं होगा? पूरे एरे का मैक्सिमम सब एरे सम 0 से 4 की बात हो रही है। प्रीफिक्स निकाल लेना, सफिक्स निकाल लेना, टोटल सम आ जाएगा 3 - 1 2, टोटल सम 2 आ रहा है क्या, 3 - 1 -3, यस टोटल सम 2 आ रहा है, बिल्कुल ठीक आ रहा है। अब मेरे को ये बताओ, क्या मैक्सिमम सम 8 आ सकता है? नहीं आ सकता यार। तो देखो इसका मतलब नहीं आ रहा, तो हमारा एल्गोरिदम ठीक है। एल्गोरिदम क्या बोला है, पहला ऑप्शन है कि लेफ्ट का मैक्सिमम सम, देखो लेफ्ट का मैक्सिमम सम कितना बन रहा है यहाँ पे, 3 बन रहा है। दूसरा ऑप्शन, राइट का मैक्सिमम सम देखो कितना बन रहा है, वो भी 3 बन रहा है। अब इन दोनों को कंबाइन करो, कंबाइन कैसे करेंगे, लेफ्ट का हमें चाहिए सफिक्स सम, जो क्या आ रहा है, सॉरी राइट का मैक्सिमम सम 5 होगा, 5 है ये तो, है ना। और इनको अगर कंबाइन करते हैं तो लेफ्ट का सफिक्स सम विच इज -1 प्लस राइट का प्रीफिक्स सम विच इज, सॉरी ये है -1 प्लस 5, तो ये 4 आ रहा है, ठीक है। तो तीनों का मैक्स क्या है 5। इसका मतलब क्या है, पूरे एरे में अगर मैक्सिमम सब एरे सम की बात करें तो सम क्या आ जाएगा 5, तो यहाँ पे क्या आ गया 5। ये बात समझ आई आप लोगों को? कंबाइन करने की बात हो रही है, कंबाइन में मैं ये देख रहा हूँ कि मैक्सिमम यहाँ से कितने एलिमेंट्स ले सकता हूँ और इधर से कितने ले सकता हूँ, ताकि मेरा सम अच्छा बने। तो इसी को हमने बोला लेफ्ट पार्ट का सफिक्स और राइट पार्ट का प्रीफिक्स। तो हमारी कंडीशन ने बताया लेफ्ट को लेना बेकार है क्योंकि सम नेगेटिव जा रहा है, तो हमने लेफ्ट से नहीं लिया, राइट से हमने मैक्सिमम सब एरे देख लिया विच वॉज 5। तो यहाँ पे क्या आ गया 5। ठीक है, तो इन 4 वैल्यूज को तुम्हें कंप्यूट करना है यूजिंग दिस फॉर्मूला एट एवरी नोड। तो क्वेरी का लॉजिक भी सेम ही होगा, ये 4 चीजें देख लो, दिस यू हैव टू डू एट एवरी नोड। तो इसका कोड तुम लोग कर लेना, ठीक है, मैंने किया हुआ है सॉल्व, मैं बस दिखा देता हूँ। ठीक है, सो इसको आईडी में ले जाते हैं। तो वही क्या, देखो जब मैं ट्री बिल्ड कर रहा हूँ, रिटर्न टाइप एक ट्री नोड है, ट्री नोड के अंदर 4 वैल्यूज रैप्ड हैं, एंड दिस इज द लॉजिक जो मैंने यहाँ पे यूज किया, बाकी सब सेम रहेगा, ठीक है। सेम चीज क्वेरी में रहेगी, क्वेरी में भी वही लॉजिक लगाया है, ये बिल्ड करते वक्त भी सेम चीज, क्वेरी करते वक्त भी सेम चीज, अपडेट कुछ है ही नहीं इसमें, अपडेट्स है ही नहीं, छोटा सा कोड है, ट्राई इट योरसेल्फ। नहीं होगा तो रेफरेंस के लिए यू कैन यूज दिस कोड 4402, ठीक है, 4402 को आप रेफर कर सकते हैं। हाँ, नो स्ट्रक्ट बना लो या क्लास बना लो, उससे फर्क नहीं पड़ रहा, यू कैन ऑल्सो मेक अ क्लास, ठीक है। क्लास बनाओगे तो एक पब्लिक कीवर्ड डालना पड़ेगा, ठीक है, क्लास बना के इनको पब्लिक कर देना, वो भी चलेगा। तो इसको एक बार देख लेना, बेस केस वगैरह फिगर आउट कर लेना, ठीक है।
Hello guys, let's start with the question K query online. So in this video we'll see the hint. We'll first understand the question, then see the hint, and then we'll also code. Okay. So let's see how we'll do it. First of all, let us try to understand this question. The question says that you are given a sequence of n numbers. That means you are given an array, and you have k queries. And there are k queries. Actually, there are q queries, and a k query is defined as a triple ij and k, such that for each k query you have to return the number of elements that are greater than k in the subsequence ai till aj. Okay, so for each query, let's say we have l and r, and then from al till ar we have to tell how many elements are greater than k, right? It's easily understood, but the main part of the question is, let me write it. So guys, main part of the question is actually the online part. Okay, this online part, that is the online query, means that you have to compute the answer of the previous query, then only you are able to compute the answer of the next query. Okay, so what happens here is, you can't store the queries, means you can store the queries but you can't manipulate them in a way. Okay, you always need the answer to the previous query to compute the answer for the current query. Okay, so let us try to understand this question first. The example here. Yes, so initially our answer is 0. Okay, I'm writing all the values here. So actually it is I, J, L, R and K and answer. These are the values that we'll be computing. Okay, let us dry run it fast. So it is actually initially the answer is 0. Okay, so initially the answer was 0. Now my I and J that I got is 2 and 3, 2, 3. So my L and my R will be equals to the I that I get, XOR previous answer, that was, let's say, right answer, and J XOR answer. Okay, so my L is 2 and my R is 3 only, because my answer was 0 initially. Okay, and K that I got is 5. Okay, so the question says how many elements are there between 2 to 3 that are greater than 5. So we can say the indexes 2 and 3 lie here. Okay, so there is only one element that is greater than 5 and it is 9, right? So the answer for the first query is 1. Let's update the answer here. Okay, now I got the I as 3 and J as 3. So guys, now my L and R will be the real L and R on which I have to work to find the number of elements that are greater than k. My L and R will be according to this function, right? So I is 3, J is 3, then L and R will be 3's, or the previous answer is 1. So 3's of 1 and it is equal to 3 is this, 1 is this, it is 2, right? 2 and J also 2. So my L and R equals to 2 comma 2 and my K was 7. Okay, so my answer is 1 now. Why? Because from in this array from 2 to 2 that is only one element that I got, and it is 9, and 9 is greater than 7, right? This is the important point to note here, is that initially if we see that from 3 to 3 there is only one element, that is 3, right? But 3 is not greater than 7, right? So the answer should be 0. But why is answer 1? Because it's an online query. I use the previous computed answer to change these values. Okay, and yes, there's also one more thing, that I have changed L to R. Okay, I also need to change my K. So my K is not 7 here, right? So my K is 7 XOR 1, which is 6, right? So my K is 6. Yeah, again the answer is 1 only, right? Because 9 from 2 to 2, from 2 to 2 we have only one element that is greater than 6, that is 9. Okay, yeah, we have to change K also, right? In the last time I didn't change K, but we have to change K. Okay, so my answer is 1 again. Now let's go for the third query. The third query is from 0 to 0. Okay, so I take 0, I take 0. Now these are my I and J. So what will be my L and R? It will be I's, or previous answer, that is 1. So it is 0 0 and these will be 1 and 1, right? And k will be actually it's 11, right? 11 is 8 plus 3, right? So 11's or 1 is 10, right? So k is 10 now. So the question says how many elements from 1 to 1 are greater than 10. So how many elements from 1 to 1? That is only one element, 8. How many elements are greater than 10? That are 0. Okay, so you see the third answer for the query is 0. I hope you understood this online part, right? So now let's think about the solution, like how we'll approach it. Okay, yeah, let's come back here. Just imagine that you have an array, and also the array is sorted. I'm just trying to give you a hint, like why would I use this. Let's say the array is sorted. Okay, let's fix some random values here. Okay, and what is the size of this array? It is actually, yeah, so the array has size of 10. Okay, I have indexed it here. Now guys, if I want to ask that how many elements are greater than particular x here, then what I can do is I can just upper bound for that x, right? For example, let's say x is 5. Okay, and if I upper bound for this I'll get this position, that's the index at 3, right? So these many elements are less than or equal to this particular x, and these many elements are greater than or equal to not equal to, they are just greater than this particular x, that is 5, right? Because the array is sorted, right? We just have to find a position that is a threshold position, that after that position all the elements will be greater than this particular x, right? So if I lower bound, I get this index 3, right? And what I do is I subtract 10 by 3 and I get 7. So 7 elements are there that are greater than this particular x. Okay, so what I have done here is I have done size minus upper bound of x. Okay, I'll code it. Okay, I'm just trying to explain you. If we have a linear array and all the elements are sorted, then what we need to do is, okay, now there's another thing that we have queries now from L to R. From L to R, how can we directly take an array that should be sorted? So what can we do is we can make a segment tree of vectors. Okay, I'll make it not this big but big. So I'm just trying to make a segment tree here, and the nodes will be big because we need them big. Okay, and let's say the base array was 5 2 1 4. Okay, so these are the base cases for the segment tree. It will be 5 2 1 4. Now there's this one thing that I need to tell is that segment tree is of vectors. Okay, so each of this node of this segment tree node is a vector, not an integer. Okay, so initially I filled the base case. Now what I need to maintain is there are two things, that the vector contains the whole range, from starting to end, right? And the second thing is that the range should be sorted. Okay, so guys, what's happening here is let me write it like this contains from 0 to 0, and this contains from 1 to 1, 2 to 2, and 3 to 3, right? I'm writing the indexes of start and end of a segment tree node. Okay, so this node will contain from starting to 1, right? So it will be actually 0 to 1, and this contains from 2 to 3. This will contain from of the whole array, that is 0 to 3. Okay, now I filled the base cases. What I'll do here is I will merge these two arrays. I already know that both my left and right child are sorted. both these vectors are sorted. Okay, so what I need to do is I need to merge them into one sorted array. So guys, remember like how did we used to merge two sorted arrays into one sorted array? By taking two pointers, right? Take one pointer I here, one pointer j here. If I is less than j, then I put I into the another array and then move I plus plus, move I forward, right? In this way I used to merge these two. And what was the complexity of merging these two sorted arrays into one sorted array? It's O n only, right? And what I can do is I will merge these. So this I will get here is 2 and 5. Similarly I'll get here is 1 and 4, and then I'll merge these two into one more. It will be 1 2 4 5. Okay, so guys, of course space will be required, but you know, we got so much we got sorted array that we needed, sorted array, and also of particular, and also of fixed ranges. Okay, so guys, if I want to query from let's say if I have a query from first index till third index, right, that means this range, then I'll query this on the segment tree, right? I'll go this way and query in this node, right? Which type of query will this be? That I already explained, this one. Now I have a segment tree of vectors and all the vectors are sorted and all the elements are increasing order, so I can directly use this upper bound function. This will take log n time, right? Not exactly log n time, log of size of this vector. Okay, so we can see these vectors are of different sizes, right? So what will happen here is now I will just query for some fixed particular range. Then I need to go at this node, because at this node we have a complete overlap, right? And I need to go at this node. For two nodes I have to apply the upper bound function and return the answer, right? Okay, let's see the code. It will be more clear when you see the code. Let's make segment tree of vectors. So initially we have structure segment tree of vectors. Okay, let's make this structure and we'll name it tree. Okay, so initially what this should contain, it should contain a vector array of integers, and let's name it segment tree, and its size should be approximately n into 4. Okay, and what else we need here is let's make a build function, okay, for this segment tree of vectors. It's void build. It has a starting, it has an end, and it has a node. Okay, so guys, we all know how to build the segment tree. Segment tree equals to if starting equals to ending. Okay, there's one more thing that I need to write it completely, because then it will say that there's an ambiguity of start and this start. Okay, there are two starts here. So start equals to end, then it's the base case. So what I need to do here is segment tree of node dot pushback. Okay, I have already defined pushback as pb. Okay, don't get confused there. A start. Okay, this is the base case. I'll just return, and my second thing is mid equals to start plus end by 2. Okay, I need to take care of this start. And then what will happen here is I'll just ask the function to build it on the left from start till mid, and 2 into node plus 1. Okay, these are my nodes. If you have any confusion regarding this function, you can refer to the above explained videos of segment tree. Okay, and then this is mid plus 1 till and 2 into node plus 2, right? So I build the left tree, build the right tree. Okay, and this is my base case, that is the leaf node of the segment tree. Now what I need to do is when I have built the left tree and I have built the right tree, I need to combine, I need to merge those two vectors into one single vector. Okay, So I can easily do it by using 2 pointers, right? So and also we have one stl function which merge to act. This is already inbuilt function. It actually merges two vectors into one other vector. Let's see how it does it. We need to provide the beginning and end of first vector, right? And similarly the beginning and end of second vector. That's the way to write it, right? It's syntax. And third is we also need to provide in which vector I need to insert it. Okay, so it's the main final vector. Okay, so let's merge it. So first we need to provide the first and end of the first vector. First vector, let's say we have a left vector, will be st node dot begin, and it will be the left subtree will be 2 into node plus 1. Okay, and also to its end, like start merging from there till here. Now we have the right subtree 2 into node plus 2 dot begin till. Okay, I've copied it, I will just paste it to end, right? So I provided the beginning and end of the first vector, provided the beginning and end of the second vector, and now I have to provide where to insert these values. So we will insert at the back of segment tree of this current node. Okay, so this was my first child, this was my second child, here it will be 2, it's right, and then I'll just insert it at the back. Okay, I hope this much is clear to you. To build this code so that we can correct some errors. Yeah, okay, so this a array was not declared in the scope, that the main array. Okay, so I've declared this, and also yeah, it is back inserter. Okay, yeah, so let me build this again. Yeah, it's completely built, no errors now. Now let's write a query function. Okay, so it will be an integer type, and it will have a start, end, l, r, a value k, and node, right? I've already discussed what are these l, r, k, and start and end. So the first case is no overlap. So if start is greater than r, right, or end is less than l, then it's a no overlap case. I return simply 0, right? There's no answer that I want from this node. And the second is partial overlap. Okay, so how to find that if the node has a partial overlap or not? Easy. If start is greater than equal to l, right, and end is less than equal to r, then this is a partial overlap case. So what I need to return is I have to find the upper bound of the array of the vector that there is in this segment tree node, and I have to return that how many elements are greater than k, right? So as I discussed above in the video, I'll do is segment tree node dot size total elements of the array minus the index of the upper bound node, right? So let me use an inbuilt upper bound. It will become starting of node dot begin till start st node dot end comma k. So this is an inbuilt upper bound function. This will return the iterator to that node, okay, to the particular point in the vector. And if I have to make it an index, then what I need to do is I'll just simply minus node dot begin, right? So if I minus anything, if I minus the beginning element of the vector with some particular iterator, then I'll get the difference between those iterators, right? And that will be my index, right? So now we have is left query, and also we have a right query, right? So it will be, let's take a mid, start plus end by 2. Okay, so this will go from start to mid, and L will be same as it is, R same as it is, K, write this 2 into node plus 1. Okay, now the other query will be right, it will be from mid plus 1 till end, right, LRK as it is 2 into node plus 2. Okay, and what I'll return is I'll return left plus right. So this is my query function. Let me build this to see if there are errors. Okay, actually this is partial overlap and this is complete overlap. Okay, yeah, so there were no errors. Now I need to copy this whole input. Now let's take input. Segment tree is built, its name is tree, right? Okay, now initially I will just take the full array. I've already declared it globally. Now what I need to do is, okay, I also need an n. Okay, now let's take m while m minus minus. These are my queries. Okay, and before these queries, let us build the whole segment tree. Okay, 0 from n minus 1 and 0, right? So my queries will be like sin I j, right, and also k. So L will be equal to I XOR answer. Initially the answer is 0. Okay, and R equals to J XOR answer. Initially the answer is 0, and also there is this value of k. K XOR equals to answer. K was actually initially declared. Let us remove it from here. Then I can write it as K XOR equals to answer. Now I have the real values of the query. So these real values are actually 1 base indexed. What I'll do is L minus minus R minus minus to make them 0 base index, because I have made a segment tree with 0 base indexing. Okay, my answer equals to tree dot query 0 n minus 1 and L R K and also 0, right? These were the values that I provided, right? And now what I'll do is see out answer. So what will happen each and every time I do this, this query okay, K also. Okay, let's take a K, L and R and K. I don't have to write int here. And what else was there? Yeah, so we got the answer. You can see the output here.
Hi everybody, this is Pulkit from Coding Vlogs, and in this video we'll be discussing this problem called Xenia and bit operations from codeforces.com. You can open the link yourself and read the problem out if you want to. I'll anyway be reading the problem out once. Xenia is a programmer and has a sequence A consisting of 2 power n non-negative integers. Okay, Xenia is currently studying bit operations to understand how they work. She decided to calculate some value v for a. Okay, the namely it takes several iterations to calculate value v. At the first iteration, here she writes a new sequence a1 or a2, a3 or a4, and so on. That it'll consist of 2 into 2 power n minus 1 elements. That is, the number of elements will be divided by 2, and it'll consist of like every or of every adjacent pair of elements in the manner a1 or a2, a3 4 a4, and a3 or a4, and so on. Okay, in the next iteration she writes the bitwise XOR of adjacent elements in the similar manner of writing the OR, and in the third again OR, then again XOR, and so on, and the process repeats until basically just one element is left, right? So if we consider an example, let's say the sequence is 1 2 3 4. She'll first write the OR of 1 2 and 3 4, and it will basically convert to 3 and 7, and then it'll she'll write 3 or 7, which is 4, so the result will be 4. Okay, We are given the initial sequence, but to calculate the value v for a given sequence would be too easy, right? We can just iterate. We can basically just simulate the process. We can for each iteration calculate the new array and go on, right? So we are given n additional queries. For each query, it is a pair of integers bp. Query bp means that you have to perform the assignment a of p equals to b. Okay, so we basically have to make a point update, and we have to tell the new value of v for the sequence, the updated sequence a, right? I hope the question is clear. You can pause and read it out once again if something is still unclear. The input format is that the input format and the constraints are the first line will contain the integers n and m and can be up to 17. So the length of the array can be up to 2 into 2 raised to power 17, and the number of queries can be up to 10 raised to power 5. The next line contains 2 raised to power n l integers, that is a1 to a2 power n, and they can be up to 2 raised to power 30 minus 1. And the next m line contain pi and bi, the index and the value of that particular and the new value at that particular index. Okay, we have to print m integers, that is the value of v after the ith query. All right, so this point onwards I'll be discussing the solution. If you want to think, you can this will be a good time to pause the video. So let's take the first example. Only one example is given. Okay, so before taking the example, let me basically tell you what I am going to do in the solution. Since there is updation involved, and we have to basically shrink the array to a size of half the current size in each step. I am thinking of making a segment tree in such a manner. Let's say let the leaves of segment tree represent the initial array. In this case, the initial array is going to be 1, 6, 3, 5 only. And if I move one step forward, one step upward, the ranges will be halved. The ranges will be doubled, right? Because these leaves contain the value or the index 1, 2, 3, 4, and these are going to contain the values for index 1, 2, 3, 4, right? And I'll simply store the OR values in the in this cases, which will be 7 and 7. Now when I move one step more upward, the value stored will be from 1 to 4, right? Now I'll simply take the XOR of these two elements, which is 0. So basically, depending on the level of the tree, if the level is the last level, then it will simply contain leaf nodes. If the level is second last level, then it will contain the OR values of the OR value of its children, right? And similarly, the next one will contain the XOR values of its children, and then again OR, then again XOR, and so on, right? So if I am to make an update, let's take the first update, which is update 1 to 4. It means that I have to update this first element, which is 1 to 4, so it will change to 4, right? Now I'll simply need to update the parents of this particular node. I am not the whole segment tree is not required to be changed. I can simply update this 7 by 4 or 6, which is 6, and this 0 will be updated by 6 XOR 7, which is 1, right? And the answer we'll have in the top node, in the root node of the segment tree, because the answer for the whole array will be contained in the root node, so it will be 1. I hope the intuition behind this is clear. So the segment tree is basically helping us to reducing the size of the array by 2 in each step, and while we move from leaf to the root, we reach our answer, right? Because we have been reducing the size by a factor of half. We have been reducing the size to half in each step, right? So to check if the current node, let's say this node, is going to have the OR of the children or the XOR of the children, what we can basically do is we can see the range of the node that it's the range of the indices that this node contains the answer for. Let's say the range of the node that the range of the indices that the current node contains the answer for has a length of say 8. It means it is the length is 2 power 3, right? So in the leaf node we had answer for the length 1. In this node we'd had the answers for length 2 power 1, then 2 power 2, then 2 power 3, right? In the first step we'll be taking the OR, then XOR, then OR. If we see, if the power of 2 is odd in this case, we'll have to take the OR, XOR, and then again OR, right? If the power of 2 is odd, then we'll take OR. Else in this case, if the power is even, in the case 2 power 2, we'll be taking XOR. So depending on the power of 2 that the length is, we can basically decide what node what operation corresponds to the current node, right? So it is simple update and simple point update and the query function. We don't even need to make the query function. We can simply get our answer from segment from the root node of segment tree. I'll quickly jump to the code once. I'll walk you through the code. I had already written it down. I have submitted it also. Yeah. So initially I'll take the number of the n and m as input. Now my total number of elements are going to be 2 power n, so I just did n equals to power of 2 power n. Then I'll take the input. I'll build the segment tree. Let's see how the segment tree is built. And before that I already initialize the sizes of the ARR and segment tree, the standard stuff. Okay, during build, if L equals R, this means I am at my root node. Then the segment tree of the current node is going to be ARL, right? L and R the nodes. L and R are the LR values of the ranges of the range that the current node represents, and ND is the index of the node basically. And if that's not the case, just split it into 2 halves, build the left half, build the right half, and let's see what is the length of the current range. And the current length is r minus l plus 1, right? Then just take log 2 to the base 2 of that, then we'll get what is the power of 2. If the power of 2 is odd, as we just discussed, then we are going to basically take OR of the children nodes. So just take the OR of the children nodes, else we'll simply take the XOR of the children nodes, right? During update, it's also very similar to what we do in standard manner. If the current index is not contained in the current range, then I'll simply return. Or if the current index is the the current range is the represents a leaf node, I'll simply update the value. Or else I'll just split the node into 2 halves and update the first half, update the second half, and then I'll see if what is the power of 2 of the current node. If it is odd, then just take OR. If it's even, just take XOR, right? So this is the manner the current the code is going to run. Let's see the sample test case. Just a second. Yeah, now it will run. Yeah, 1333 is the answer. This is the submitted code. It is correct only. I hope the intuition behind the solution is clear. How I reached to the fact that I'll be using a segment tree for this, and I hope the code itself is clear. Thank you. That's it. This is it for this video, guys. Thank you.